Hello.
Hello.
তুমি হ্যালো করলে আমাদের কাছে
অর্ণব স্যারকে ছাড়া বাকি নিজেদেরকে ফোন এবং নিজেদের ভিডিও অফ রাখুন।
হ্যালো হ্যালো
অর্ণব স্যার শোনা যাচ্ছে কথা?
হ্যাঁ, আমি শুনতে পাচ্ছি, বলুন।
হ্যাঁ, আপনি শেয়ারে গেছেন, শেয়ার কন্টেন্ট।
হ্যাঁ,
ওখানে দেখুন শেয়ার স্ক্রিন 1 বলে আছে।
শেয়ার স্ক্রিন অন আসছে।
শেয়ার স্ক্রিন বলে কিছু পাচ্ছেন না?
দেখা যাচ্ছে? দেখা যাচ্ছে?
বাকিরা নিজের সবাইকে একটু আনমিউট রাখুন। মিউট।
তুমি সেন্ট্রালি আনমিউট করে দাও, মিউট করে দাও।
দেখা যাচ্ছে?
অন করেছেন?
শেয়ারিং স্টার্ট।
কি কি আসছে বলুন আমাকে একবার।
শেয়ার স্ক্রিন করলে শেয়ার কন্টেন্ট একটা আইকন খুলছে। স্ক্রিন 1, ওকে। স্ক্রিন 1 এসছে।
আসছে। আপনার শেয়ার স্ক্রিনটা হ্যাঁ স্যার, আপনার স্লাইড এবার এটাকে আপনি শেয়ার করবেন, আপনার এই উইন্ডোটা সকলে দেখতে পাবে। ওকে স্যার।
উইন্ডো স্লাইড দেখা যাচ্ছে?
হ্যাঁ হ্যাঁ দেখা যাচ্ছে।
ওকে।
ঠিক আছে স্যার, বুঝেছেন তো কিভাবে করছেন?
হ্যাঁ 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 ঠিক আছে।
ঠিক আছে, তাহলে এবার আমি মিটিংটা শুরু করি এবার।
হ্যাঁ হ্যাঁ
বেশ, সবাই কাইন্ডলি একটু মিউট রাখবেন।
So, a part of such an effort, I'm hopeful that this webinar will certainly prove to be a milestone towards academic goal of this college. I hope this webinar will be a grand success. The topic of the webinar, recent advancement in chemical sciences, is certainly interesting. Both, I think, the students and teachers will be benefited and updated through this webinar. I will not take much time as everybody is waiting to listen to the enlightening speech of speakers. So I wish a very good evening. My best wishes to all. And with these words, let me take leave of you. Thank you all. You all? No, sir.
Thank you, Dr. Arunoday Mukherjee, IQC coordinator. May I now request our principal, Dr. Arup Kumar Maiti, to welcome the chief guest and welcome the participants. And please deliver your welcome address, sir, please. Arupda. Arupda, please.
Sir, I think Arup sir is not joined yet.
Arup Kumar Maiti.
হ্যাঁ আছি।
হ্যাঁ বলুন প্লিজ।
শোনা যাচ্ছে?
Yes, yes.
দেখা যাচ্ছে তো? ঠিক আছে?
Host admin, please present Arup Kumar Maiti in the pick line front page, please. AKM Arup Kumar Maiti.
Arup sir, please turn on your video.
Your video is
Please,
off.
yes.
ঠিক আছে?
Now it's okay. Yeah, please.
Okay.
Ahead.
Okay. My heart leaps with joy to find an opportunity to welcome the participants of the international webinar organized by Department of Chemistry of RANAGHAT College in coordination with IQAC. I accord a warm welcome to the distinguished speakers, Dr. Arnav Ghosh, Dr. Somnath Bokshi, and Dr. Taposh Ghosh, who have done us great favor by giving consent to enlighten us with their talks through webinar on recent advancement in chemical sciences. All of us are aware that COVID-19 and lockdown hamper the regular academic activity. For this reason, we have to carry on academic activity online. As a part of this effort, the teachers of Department of Chemistry have come forward to organize the webinar with their sincere effort in this challenging time. I am greatly thankful to them. I am also thankful to the members of IQAC and other supporting staff who have played an important role in organizing the international webinar today. As the head of the institution, I always encourage teachers and students to find new avenues of teaching and learning. I am fortunate to get positive response from all quarters. I am sure that participants will be greatly benefited and updated today through the webinar. Let me convey my best wishes to all. With these few words, I am taking leave of you. Thank you.
Thank you, Principal Dr. Arup Kumar Maiti, for his warm welcome address. May I now request our head of the department, Dr. Swapun Maji, to introduce our first speaker, Dr. Arnav Ghosh, Assistant Professor, IIT Kanpur. Please, Swapun Maji, sir.
শোনা যাচ্ছে?
Yes, yes, go ahead, please.
Good afternoon, everyone. Welcome to this international webinar on recent advancement in chemical sciences. Before we begin, I would like to thank Dr. Arup Kumar Maiti, Principal, Dr. Arunoday Mukherjee, ICAC Coordinator, and Dr. Habibur Rahman, Convener of the Organizing Committee, for organizing this webinar. I would also like to thank the speakers, Dr. Arnav Ghosh, Dr. Somnath Bokshi, and Dr. Taposh Ghosh for spending their precious time in preparing the lectures for the webinar. Last year, our chemistry honors department completed 50 years. We were planning to hold a seminar like this to celebrate the Golden Jubilee, but it did not happen for various reasons. Let us have a delayed Golden Jubilee celebration to this webinar. Our next speaker is Dr. Arnav Ghosh, Assistant Professor, Indian Institute of Technology, Kanpur. Dr. Ghosh did his PhD from Indian Association for Cultivation of Science, Kolkata, in 2015. Then he went to Israel for doing his postdoctoral research work in Weizmann Institute of Science from 2015 to 2019. At present, he is Assistant Professor in Indian Institute of Technology, Kanpur from March 2019. His specialization area is non-equilibrium statistical mechanics, quantum system, and quantum thermodynamics. Research interest area of Dr. Ghosh is statistical mechanics of Fermi ion system and quantum thermodynamics. His today's popular talk is quantum thermodynamic machine. I hope the audience, especially our beloved student, will enjoy and learn from these lectures. Now I request Dr. Arnav Ghosh, please begin his lecture. Thank you. Please, Dr. Ghosh.
You. Okay. Hello. Hello.
স্যার আপনাকে শোনা যাচ্ছে স্যার।
Yes, please
Okay.
go ahead.
Okay. So, okay. First, I would like to thank the organizer for the invitations and thank you for the kind introduction. So today, the title of the talk is Quantum Thermodynamic Machines, and here is the outline. So first, I would like to give you a general introduction to quantum thermodynamics, and then I will discuss 3 of my recent works that I did during my postdoctoral period before joining to IIT Kanpur. And finally, I will conclude. Now, by quantum thermodynamics, what we mean is that in one line, I would say that quantum thermodynamics goes beyond traditional thermodynamics by accounting for effects imposed by the laws of quantum mechanics. Now, what do I mean by that? Yes, okay. So from our school days or college days, we are familiar with the thermodynamics. That thermodynamics is the equilibrium thermodynamics that we study. And although we call it thermodynamics, you remember that there is no dynamics into it. Now, when we call quantum thermodynamics, okay, the term quantum, the fundamental equations of quantum mechanics is the Schrödinger equations, and therefore in quantum thermodynamics, when we see quantum thermodynamics, it brings a dynamics into thermodynamics. So essentially, we are interested into the dynamical behavior of any systems. Here in particular, any quantum systems, how it evolves, how it to equilibrium thermodynamics. I mean to equilibrium in particular. So all these finite time thermodynamics, the quantum thermodynamics, the basic purview is that how the systems, I mean the dynamical evolutions of such systems. Now, although the term as it suggests may appear that it is a very recent, new term and a new topic of research, but I would at the same time should mention that the relations between quantum mechanics and thermodynamics is not that new. Okay, so if we recall the early development of quantum mechanics, for examples, the Planck's blackbody radiations, Einstein's photon concepts, or spontaneous emissions, these are examples of excellent thermodynamic argument where that played a very important role in the early development of quantum mechanics. But for some reason or others, these two disciplines after that, for many decades have been developed very separately with few exceptions. And one important exceptions in our context is these three-level lasers at heat engines proposed by Scoville, Schulz, Dubois in late 1950s. So this is an important work in our context, but I'll discuss this in details. But before discussing this, let us first start with a very, what we know we are much familiar with. What we are much familiar with is the thermodynamics than quantum mechanics, because we know that thermodynamics was there for 18th century, whereas the quantum mechanics only developed in last century. So we are much more familiar with thermodynamics, and we all know that thermodynamics applies to large macroscopic systems consisting of many degrees of freedom. Okay, so where the thermal fluctuations are neglected, and we are mostly interested with the average values of the thermodynamic quantity. Okay, now the point is, when we go down the scale, okay, am I audible? Hello? Okay,
You
so
you are very much audible.
okay, thank you. Yeah,
But
okay.
when you
Can I
want
see
to
your slides?
Sorry,
Your slides.
slides are coming.
no, slides are not coming actually.
Really?
You have to share this one.
No, it was not. This is, you can see the slides.
No, sir. You go to the share option. Share
I
content.
shared it already.
Sir, it's coming.
Now coming?
Yes. Please continue, sir.
Okay. Okay. Oh, sorry. It's okay now? Hello?
Yes, sir. It's okay. It's fine.
It's okay now, Arnav. Go ahead, please.
Okay. So okay. So so just a quick summary that this was the outline, and this is the first slide that I mentioned. Okay, as the brief introduction to quantum thermodynamics. And so as I said, that we are much familiar with the thermodynamics, and we know that the thermodynamics applies to large systems, large macroscopic systems, where we can neglect the thermal fluctuation. Thermal fluctuations are neglected, and we are mostly interested with the average values of the thermodynamic quantity. Now the question is, what happens if we go down the scale? Now, if we go down the scale, we reach small systems such as macromolecules with fewer degrees of freedom. Now, the thermal fluctuations are no longer neglected compared with their average values. Then one needs the theory of Brownian motion to describe such systems. Okay, and interestingly, 2016 Nobel Prize in Chemistry was awarded for in this regime for designing and synthesizing molecular machines out of macromolecules that we all know. Now, it gives a hint towards the importance of designing and creating smaller and smaller devices. Okay, and it is quite evident that if we go down the scale and eventually reach at quantum scales, then quantum systems with quantum degrees of freedom, okay, such as quantum superposition, coherences, these will play a significant role on the performance of the quantum machines. So therefore, this regime has attracted a lot of attentions in recent times and has been highlighted in all sorts of scientific magazines. So this is the domain that I am going to talk about in next of rest of my talk. Okay, so up to this point is clear, hopefully. So okay, so now this recent field, I would say, roughly started around 2003, when Marlan Scully, Sohail Zuberi, G.S. Agarwal, and Herbert Walther came up with a very nice idea that it is possible to extract work from a single heat bath using quantum coherence. Now, you see, this is a very bold statement, because we already know from our basic thermodynamic knowledge that it is saying that I can extract work from a single heat bath. Okay, then I should evidently mentions that it does not mean that it violates the second law, the laws of thermodynamics, in particular the second law of thermodynamics, which we know forbids extraction of work from a single heat bath under cyclic process. But it is possible, still possible, in quantum regime using quantum coherence. Now, this is a remarkable result, and this motivates not only theoreticians but also experimentalists to build heat engine. Okay, and eventually in 2016, experimentalists have done that, built a heat engine out of a single atom, or refrigerator out of trapped ions. Not only that, in last year, a group of researchers from Oxford has managed to show that quantum coherence or quantum superpositions or between states, various states, may lead to power boost for quantum engines over their classical counterpart. Moreover, experiments have been performed to show that a nano engine can surpass the Carnot bound, okay, with a vibrating nanobeam. So the experiment has been done with a vibrating nanobeam interacting with a quantum bath, exotic quantum bath. In this context, we have also done some work. So I will come back to this point, but I would like to say that this is just to give you some idea about the kind of work that has been done in last few years or 10 years and so in this field. And last year there was a very good review has been published from Spinger, highlighting the central results and works. And fortunately, we have also contributed a chapter in this book. So the questions that we have addressed there is the following: that how do quantum resources affect the power or efficiency of quantum heat machines? What are the general rules and performance bound of such quantum heat machines? What is the role of quantum fluctuations, which is fundamental and therefore should always present at quantum scales? I expect that after this talk, Somnath will also speak about fluctuations, which is very important, the role of fluctuations and noise in biological systems, Here I am going to discuss the role of quantum fluctuations in performance of the quantum machines, and finally the role of the what are the practical implementations. So these are the important questions that we have tried to understand throughout our work, and that I would like to share with you now. Okay, so with this background, let us go to the original model of the three-level measure proposed by Scoville, Schulz, Dubois in 1950s. Now, this is a very important model because this can be considered to be one of the first examples, known examples of any heat engine with discrete energy levels. Usually in classical engines, we don't consider the discreteness of the level systems, but this is the first examples of discrete energy levels. So this can be thought of as the first examples of heat engine. And it was much earlier. So these peoples are much ahead of time. And now recent times, this model has gained a lot of interest and various applications. But this is the first examples of discrete energy level. So this can be thought of as the first examples of heat engine. Is there any echo somehow? Much earlier. So these people are much ahead of time.
Yeah, some sounds are coming. I don't know, but please, I request everybody.
Okay. So here is the Scoville-Schulz-Dubois model. So this assumes the conversion of heat to work, and this consists of a photon absorption from a hot bath at nu p, re-emission of a photon at nu I into the cold bath, and production of a signal photon nu s at the difference frequency. Therefore, the efficiency of such devices becomes the output energy divided by the input energy, that is nu s by nu p. Now you can see that this three-level model resembles to any known maser and laser devices that we are familiar with, where a population inversion is required for laser or maser amplifications. And the population inversion is created in all practical situations by the hot bath, which is usually realized by some external pump. Okay, and this pump, what it does, it pulls the population from level 1 n1 to n3 such that the populations of level 2 becomes larger than the population of level 1. That means you have a population inversion between level 1 and level 2, as shown in the diagram, with the length of the energy levels proportional to populations. Now, Scoville-Schulz-Dubois model states that the efficiency, if the population inversion prevails between the level 2 and level 1, that is, if n2 greater than n1, then the efficiency of such devices is always bounded by Carnot. Okay, now you can prove these results just by elementary maths. Okay, what you have to do, I just take this from the original paper, that is n2 by n1. You have to write n2 by n1 by is equal to n2 by n3 times n3 by n1. What is n2 by n3? These two levels interacts with the cold bath, thermalized with their Boltzmann populations. Same for n3 by n1. These interacts with the hot bath, with thermalized with their temperature and frequency. So once you multiply this Boltzmann factor and rearrange it little bit, you get equations 3. Now here, this nu p by nu s is basically the inverse of the measure efficiency we defined, eta m, and what is T1 minus T0 by T1 is basically the Carnot efficiency. Now, in order to have this n2 greater than n1, we need this factor inside this exponential has to be greater than 1, and this immediately gives us these conditions that eta m has to be less than eta C. Now you see this very simple analysis of semi-classical treatment gives us a remarkable results, and therefore this model has now become a canonical model for understanding a wide variety of heat engines and refrigerators considered now in quantum thermodynamic community. But at the same time, I would say that this semi-classical treatment of the model assumes one thing. It assumes that all the energy acquired by the signal mode, I can extract it in terms of useful work. But this is no longer true for quantum signals of small amplitude. For that, we also have to take into account quantum fluctuations. And these fluctuations are like noise. So therefore, they will hit up the signal, and therefore a part of signal energy cannot be extracted as useful work. Okay. Now to explore this fundamental issue, we consider a very similar model to the original Scoville-Sulz-de-Bois model, that is the following. We consider this model where we consider, that is, what do I mean by similar model? That is, we also consider that the working medium is simultaneously coupled to both cold and hot bath with appropriate filters, which passes only the required frequencies. Okay. But now there is a difference also between our model and the original Scoville-Sulz-de-Bois model, which makes our model very distinct from the original model. In our model, we don't need the population inversion to get the signal amplifications, because it assumes that the working medium resonantly and therefore more strongly coupled to the cold bath than the hot bath. That is, gamma C is much greater than gamma H. Therefore, what happens? This working medium, since it is strongly coupled to the cold bath, it attains its steady state mainly determined by the cold bath temperature and population. So it attains its steady state, not equilibrium states. Now, what happens at steady state? At steady state, the thermal imbalance between the hot bath temperature and populations and the cold bath temperature and populations behaves almost like a inverted two-level systems for the signal mode, and which leads to its amplification, signal amplifications. Now this happens because the working medium interacts with the cold bath with one photon transitions. Okay, just with say G to E, it is coupled to cold bath with omega 0, whereas it interacts with the hot bath with two photon transitions. So it absorbs omega 0, emits signal photon at frequency nu, and also this omega 0. That means absorptions of a hot bath photon nk to nk minus 1. Okay, so absorption of a hot bath photon creates a signal photon ns to ns plus 1, and then excitations in the working medium G to E. Okay, so you basically have this psi I start with psi I end up with psi f. Now using first and second order perturbations theory, one can show that this entire process can effectively be realized with a effective Raman Hamiltonian of this form VH. Okay, that is absorptions of a hot bath photon creates a signal photon and then excitations in the working medium, or vice versa. Whereas the interactions with the cold bath occurs through usual interactions, that is absorptions of a cold bath photon creates an excitations in the working medium and vice versa. Now I would say this scheme is very universal in the sense that I can always choose my working medium frequency to be resonant with the cold bath, and tune the signal frequency at the difference between hot and cold bath frequencies such that it gets amplified at the expense of the difference between hot bath photon occupancy and the cold bath photon occupancies. Okay, now using these interactions Hamiltonian, one can derive the master equation. So I am just mentioning these few technicalities for completeness. Now, once from these master equations, one can derive the average dynamics of the signal modes. Here you see this rho EE and rho GG, they are the populations of the ground and excited levels. And as you can see, this rho EE by rho GG is NC by NC plus 1, that is NC and NC. These are the Bose distribution factors. So one thing is clear, that the populations of the excited states is lower than the ground state. That means we do not require, there is no population inversion in the working medium. Still, we can have these signal amplifications. Now, one can notice that this +1 factor in this expression, this +1 factor is due to spontaneous emissions, and it is completely quantum mechanical in origin. If we neglect this +1 factor, then we can treat the signal semi-classically. Then we can replace Ns by its intensity. Then we recover the Scoville-Sulzberger results, that is, the efficiency is bounded by Carnot. But if we don't neglect this +1 factor, then we have to treat the signal complete quantum mechanically. Then one arrives at the following expressions for the efficiency. This is the expression one obtains. Now one can see there is a thermal factor appears in the denominator, and this thermal factor, being a disordered form of energy, cannot be extracted as useful work, whereas only this mod alpha 0 square, this is the coherent component or the ordered component of energy, can be extracted as useful work. Now one can also see that if mod alpha 0 square is much larger than this thermal component, then one can neglect this thermal component. Then what would happen? This numerator and denominator almost cancels each other. Then the efficiency approaches the semi-classical SSD efficiency, and that exactly we obtained from the, as you can see from the diagram. That is, for larger value of mod alpha 0 squares, for large signal amplitudes, for classical fields, these approaches we basically get the SSD efficiency. But for small amplitude, we have to take into account these quantum fluctuations, and these quantum fluctuations is responsible for degrading the machine performance. So what essence I said, so what does it mean? That although I said this model, in this model we can get the signal amplifications without any population inversion, but at the same time it says that for small amplitude quantum signals, these quantum fluctuation, thermal fluctuations, are responsible for degrading the machine performance. So the natural question is there a way to boost the output power or efficiency of such quantum machines? And in this context, we explore the possibility of quantum catalysis in heat machine setup in presence of a weak nonlinear pumping. Now, this is very analogous to chemical reaction catalysis, where a small amount of catalysis, presence of a small amount of catalyst, can enhance the reaction rates but remains unaltered, unaffected before and the end of the reactions. In the same way, the intensity of this external magnetic, the external pumping, nonlinear pumping, remains unaltered before and end of the process, but the output power get enhanced. Now, without going into any technical details, let us understand very qualitatively. Okay, so here is the distribution, phase space distributions of the output signal in presence or in absence of nonlinear pumping. That means in presence of pumping means this kappa is not equal to 0, where this kappa is the strength of the nonlinear pumping. Is kappa is 0, that means there is no nonlinear pumping. Now we can see that both this output signal is broadened, and this is broadened, as I mentioned, due to these thermal fluctuations. These distributions get broadened. Also, we notice that both these distributions are not centered at the origin. They are displaced from the origin, and we know that any thermal distributions which is centered at the origin, it is in its lowest energy Gibbs state, and therefore we cannot lower its energy further. And this is why we cannot extract any work from a single thermal bath. Now any thermal distribution. Hello.
Yeah, hello. Hello.
Hello.
It's audible.
Hello.
Yeah, it's audible.
Yeah,
Yeah,
sure.
audible.
Okay, thank you. Okay, so any thermal distributions which is not centered at the origin is therefore not in its minimum energy state, and therefore it is capable of delivering work. So in this sense, both this output signal is capable of delivering work. Okay, now the question is, which is capable of delivering more work? Okay, obviously this one, isn't it? Because this is displaced as well as squeezed, therefore it has a more energy content than this one, and therefore it is capable of delivering more work. Now you may question that, okay, although it can deliver more work, but in this case I also have this injected pump intensity, and this is expected to contribute to the output power. Okay, and therefore it will enhance the output power intensity, or the output work. But so to make the comparison fair, what we did, we subtract the invested pump energy and plot the net output power. Still we see that in presence of nonlinear pumping there is a power boost. Okay, the output power is still much larger than in absence of pumping or in presence of linear pumping. Now, this is because of the nonlinear nature of the pumping contributes to output in nonlinear fashion, whereas a linear pumping contributes to the output in a linear fashion. Therefore, upon subtracting the pump energy for linear pumping, its effect gets cancelled out. Whereas for a nonlinear pumping, because of the nonlinear nature, okay, of the pumping, a net effect remains even after subtracting the invested pump energy, and therefore we get this power boost for nonlinear pumping. Okay, now in this plot, this point corresponds to represents the point, this point represents the efficiency at zero power, that is which corresponds to the Carnot bound. Okay, so even in this case, although we get the output power becomes larger in presence of nonlinear pumping, still the efficiency is still bounded by Carnot upon subtracting the pump energy from Wmax. Okay, what is Wmax? Wmax is the maximum extractable work, okay, which is given by the energy difference between this output signal and their corresponding thermal energy, and their corresponding thermal energy. energy thermal states. Now, this energy difference we have to calculate under unitary process. Now, why unitary? Why we need these conditions of unitarity? Now, this goes to the concept of passivity. Okay, so this is a very important concept. So let us spend few minutes on it, and then I will come back, because this concept is useful to derive the efficiency bounds for quantum baths. Okay, so what does it mean? That here is the basic idea. Say, consider we have a quantum mechanical state rho with their respective energy eigenvalues. So these are the energy eigenvalues. Okay, now I am interested in what is the minimum energy state that I can obtain from this rho. Okay, now the minimum energy state can be obtained from rho by reshuffling the energy eigenvalues in a monotonic decreasing order. Okay, so this is the state pi is the minimum energy states that you can obtain from rho. Now the energy difference, that is H average of rho minus H average of pi, now this entire energy difference will entirely contribute to work from our basic thermodynamics. We know if the process is isentropic. Now this happens if one obtains from rho by unitary process, because the von Neumann entropy, quantum mechanical von Neumann entropy of the two states are same if the two states are related by unitary transformations. Okay, so this is because of reason we need these conditions of unitarity. Now this W max, the maximum extractable work, is also called ergotropy and denoted by this symbol delta W, and because this is the maximum change in energy that can be affected without any change in entropy. Therefore, it is also called ergotropy, that is the maximum change in energy without any change in entropy. And by the definitions, the way it is defined is always positive, because the energy of the state pi is always less than the state rho. Okay, and the state pi is called the passive state of rho. Okay, because you can no more lower its energy. This now you can understand, this is a very general concept. Okay, so for examples, the thermal state is just an examples of passive state, but the passive state itself is a much more general concept. Okay, in equilibrium thermodynamics that we are familiar with, we always speak about thermal baths. Okay, we do not have anything else, but in quantum mechanics you can have different kinds of baths. So you need not only the thermal state, you need a more general kind of descriptions, and this is what we need for passive states. So for examples, as I said, the thermal state is just an examples of passive states, but there could be other state which is passive but may not thermal. For examples, the ground state of harmonic oscillators, the vacuum state, it is a passive state, but it is not thermal. Okay, now any non-monotonicity, okay, of the energy eigenvalues makes the state non-passive or active, and therefore capable of delivering work. Okay, so and just let us note that the way we define this ergotropy is always positive. We need these conditions to derive the efficiency bound relations. Now, just a small side remarks that how do you implement this unitarity in practical situations? I will not go into in details, but this can be very simply be implemented by using a beam splitter transformations. Okay, now the beam splitter transformations, this transformation property is essentially unitary. It's what it does, it basically separates. If you have an output signal mode, it can separate from its total energy, it can separate the thermal energy or the passive energy or the coherent energy and separate it out into different ports. This is how you can implement these unitary transformations in practical situations. But okay, so now let's go back to where we are, that how this concept of passivity or ergotropy helps us to obtain the efficiency bound for various quantum bars. Okay, here is the situation. When the heat changes, the hot bath is replaced by a non-thermal bath. What do I mean by non-thermal bath? In the catalytic engine, we consider the working medium is interact with the thermal bath, and we have an external pump to supply the work. But you can have, in quantum mechanics, you can have a different kind of baths rather than thermal baths, which can provide the thermal energy as well as the ergotropy in the form of work. Now you can immediately understand this kind of baths, using this kind of baths is more advantageous than the catalytic heat engine that I discussed earlier, because here the entire heat as well as the ergotropy in the form of work is solely supplied by the hot bath. Now if someone goes on deriving the efficiency of such non-thermal baths, he or she may end up if they use the definitions for the derivations of the efficiency, the output energy divided by the input energy obtained from the hot bath, then he or she may obtain an efficiency which is above Carnot, and that exactly happens when a nano engine interacts with a squeezed thermal baths. Okay, this is called, this non-thermal bath, sometimes called the squeezed bath, because the phase space distribution is not circle, it is squeezed, it is ellipse, and therefore and this exactly happens. Experiment has been done with vibrating nanobeam interacting with a squeezed thermal reservoirs, and there the efficiency approaches above Carnot. So the natural question is, what does it mean? Does it mean that for quantum baths the Carnot bound is violated, or does it simply means that the Carnot bound is not at all applicable for quantum systems at the quantum scales? Now our analysis reveals that none of them are true. We derive an efficiency bound which is applicable for both the quantum as well as classical baths, and the efficiency expressions is given by the following, where we can see in the denominator we have an ergotropy term. Now for thermal baths, this ergotropy, as you can understand, this is 0. Therefore this numerator and denominator exactly cancels each other, and we recover the standard Carnot bound results. Whereas for non-thermal bath, the way we define the ergotropy, this ergotropy is always positive, and this makes this factor less than 1, and therefore the efficiency may becomes above Carnot, and it is only bounded by 1. Okay, but it is nothing to do with the violations of the Carnot bound, because the Carnot bound that we study in classical thermodynamics is, in classical thermodynamics we have only a thermal baths, but in quantum mechanics you can have very exotic kind of baths. For that you need to derive the efficiency expression slightly differently, and this is what have been done here. Okay, now there is another twist. We also see in books that all reversible engines has maximum efficiency, and that is Carnot. Now if one go on to derive the efficiency bound using the reversibility criteria, that is this eta sigma, one may end up with an unphysical efficiency bound above 1. Okay, now this happens exactly because of the same reason. That the reason is the following, that the maximum efficiency of any quantum engines, be it classical or quantum, it is always governed by the maximum entropy principles. Okay, So the maximum efficiency of any engines, be it quantum mechanical or classicals, it is given, it is obtained, the maximum efficiency obtained if no ergotropy is dumped into the cold bath or no entropy is generated within the engine. Now for thermal baths, okay, so what does it mean? That is the minimum energy dumped into the cold bath. Now for only thermal bath, this minimum energy dumping and the reversibility criteria coincides, but these two criteria are in general may differ, and that exactly happens for quantum baths. So our analysis reveals that the maximum efficiency of any engine, be it classical or quantum, is obtained by the least energy dissipations over the engine cycles, not by the reversibility criteria. So the maximum efficiency, the bound is not governed by the reversibility criteria, but the minimum energy dissipations over the engine cycles. Only for thermal baths, these two criteria coincide, but they are not in general identical. Okay, so with this I would like to conclude that as I have said, we have proposed a minimal model for quantum heat machines without which can work without population inversions but still can give rise to these signal amplifications. We have explored quantum catalysis in heat machines setup by nonlinear pumping and derive efficiency bounds for non-thermal engines. With this, I would like to conclude by saying the famous quote of Albert Einstein's that the thermodynamics is the only physical theory of universal content which I am convinced will never be overthrown within the framework of its basic principles or applicability. So with this, I would like to conclude. I acknowledge my postdoc supervisor Gershon Kuriski and other collaborators, Kali Davidovich Lvovsky. Okay, and thank you for your kind attentions. Thank you. Thanks a lot. So if you, I'd be happy if there is some questions and so on. Thank you.
Hello, Arnob. Hello.
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 Yeah, so it's a very nice lecture, and thank you very much for your nice lecture.
Okay,
Before any seat to
yeah,
process the discussion, I request you to please switch on your video, please.
yeah. No, wait a minute. It was on. It was on, but somehow it is
Yeah,
switched off.
somehow it was in the
Okay.
meantime. Somehow it's switch, and then the video. You see in the below, just below there is a sound system, and then video.
Your top of the screen, you see the bar. There you stop the sharing. Stop the sharing.
Okay, sharing.
Yeah. Now it's okay.
Okay.
Yeah, so I would request also to the participants from the different disciplines, especially from physical chemistry or inorganic chemistry, and the faculties request to, if you have any doubt or queries or questions, then please, the question is open for audience, please.
I think there is some questions already.
Yeah, so if anybody has the questions, so please unmute your box and then you can directly ask to the question to Dr. Arnab Ghosh.
Okay.
Anybody?
So there is, I can see one question is written there. The question is the quantum heat engine can be made practically and how? Okay, the answer is okay. I already gave several examples of practical examples where the experiments have been done. The references are given there. Okay, so usually these kind of heat engines has been, the experimental groups are mainly from quantum optics. So these experiments can be done in a very controlled way, in basically in some optical cavities. okay, where you shine the heat bursts are there, basically behaves like the laser lights, okay. In the nano engine cases, the heat bursts are modeled by electric signals and so on. So there are various means. I mean, the working medium, there are NV center diamonds. So various things are there by which you can model such kind of quantum engines. Yes, but still it is very in its basic level. So the experiments only started only 2 to 3 years. So it is not that effective, but it's still in principles is doable.
Yeah, thanks. I can also see on a second question. What does the term quantum coherence mean?
Okay, so yeah, so the quantum coherence, I mean, this is slightly tricky. Okay, so I have to describes these things in a, well, say when you have, once you have a quantum mechanical systems, you have various energy levels, okay. And then you can form a matrix, okay. So say think of a matrix, okay, and you just think of a 2 by 2 matrix. So let's consider a 2 by 2 systems, just a 2 level systems, okay. Just the ground levels, say atoms or molecules, you have only the ground levels and the excited levels. When you write down these systems in complete quantum mechanical form, you have 4 terms in the matrix. You have the first element, second element, third element, and the fourth element. The diagonal gives you the populations of the ground and the excited levels, okay, whereas the off diagonal gives you the coherence terms. So these are the basically the off diagonal elements of the matrix matrix, okay. So I mean, very naively speaking.
Yeah, so there is an interesting term, non-thermal bath. So, Dr. Arno, please.
Okay,
Yeah, how can
so
one
as
generate a non-thermal bath?
okay, so there are various means. I mean, usually in classical thermodynamics, we always consider a thermal bath. There is nothing non-thermal. But in quantum mechanics, you can have such kind of baths where you can generate. As I said, once you have a thermal bath, so it's kind of the form is Gibbs state. So it is e to the power h by kt. Okay, what is h? H is the total energy. Okay, now think of the harmonic oscillator cases. So you have kinetic energy and the potential energy, and both are square, p square plus x square. Now in the phase space, since both are quadratic, the distributions looks like a Gaussian, okay. So you have a Gaussian distributions, or if you take a cross sections, it becomes a circle. Okay, now as I have shown in the slides as well, the non-thermal baths, the phase space distribution. So this is the kind of a phase space distribution, is not circle but rather a squeezed one. Okay, so in one quadrature it becomes smaller than the others. Now how to generate this kind of bugs? So this can be also one can generate such kind of bugs using again optical cavity. What you have to do, you have to put some nonlinear element, okay. So chi to medium, okay. So if you have a NLO or NLO systems, you put it, then you can generate using these systems. The output signal, if you plot this phase space distributions, it doesn't becomes a circle, it becomes a quizzed, okay. So in one quadrature it becomes a quizzed, okay. So this kind of distributions you can generate. So if, for examples, in the nano engine case experiments, people have generate this using electrical signals, okay. Sine wave and cos wave, they superpose it, and using various combinations they generate these kinds of non-thermal bath. Okay, so it is basically, well, it doesn't mean that it does not have any temperature. What it means that in usually thermal baths, the properties of the baths is entirely determined by the single temperature T and the frequency. Whereas for non-thermal bath, you have some extra parameter R, usually denoted as is called the squeezing parameter. The way which you you basically squeeze this distribution in this space. So it is a two parameter distribution, not only the temperature but also you have another parameter. Okay, so usually in this community sometimes it is called the non-thermal, also it is called squeezed thermal. Okay, so both terms are used. I mean, there is nothing
Yeah, it's I don't know whether it is very relevant or not, but this is the last question that we can take because our time is
Sure.
so. Is this engine can be used our regular life, and how can it improve our living style?
Well, okay, so right now this is just right now this is very preliminary. Well, I don't know, maybe I mean the idea is that the classical, I mean okay, maybe if I say in this way it would be easier to understand. Okay, the Carnot bound only gives you the universal efficiency bound. It says that the efficiency cannot be greater than Carnot. It is always bounded by 1 minus Tc by Th. Now, it is also true that for ideal Carnot engine, it corresponds to the efficiency corresponds to the 0 power. So essentially, it doesn't make much sense, okay, to build if it have an ideal engine. So essentially, in all practical situations, you need an engine with a finite power. Okay, so say for examples, all these solar cells and all these things which are used in all practical engines, the efficiency is much less, maybe maximum 18 to 20 in solar cells also. So the idea is can we use, because from our basic understanding of quantum mechanics, we have seen that quantum mechanics always provides some rules to bypass the what is allowed by classical mechanics. So so can I use some basic some advantage from quantum mechanics to have a greater performance in terms of power or efficiency that is allowed by the classical engines? So this is the whole idea, but it is still very preliminary at this stage. There are various theoretical proposals, some experimental efforts is going on. It has to be tested over a long time, then only I can say that when it will be, maybe after 50 years, and so maybe 20-30 years. So hopefully this is the expectations. But if it is so, if it is doable, then definitely that would be another advancement and another revolutions. For examples, also you may be heard of these quantum computers. So also these it's also a quantum computer is also, you can thought of as an engine. Okay, it's a better performance. I mean the conventional the quantum computers, we expect that the quantum computers will perform much better than the classical computers. But again, this performance will be governed, can be studied using these basic principles as well. Can we
Okay.
improve their performance? So that's
Okay.
the whole thing.
Yeah. Thank you, Dr. Arnav Ghosh, for your nice and lucid and very. I think it's an imaginable. I mean, it's movable. I mean, it's an very understandable and very nice talk. Thank you very much with
Thank
this
you
presentation.
so much.
So on moving forward, may I now request Dr. Joita Datto, my colleagues, to introduce Dr. Somnath Bakshi for his presentation. So please, Dr. Datto, please.
Okay, so may I now switch off
Yeah,
my video?
yeah. You can leave the sharing. You just do one
Yes,
thing: stop
that
sharing.
I stop. Yeah,
Yeah,
that I stop. Yeah.
yeah.
Okay, thank you.
Okay. Yeah. So, Dr. Joita Datto, please. May I now request Dr. Joita Datto? Joita? Hello? Joita? Well, I think it's a connection problem. Joita Dotto is not here. So,
Hello.
yeah, Joita, please.
Hello.
Please switch
Yeah,
on your video, please.
yeah, sure.
Yeah. Now it's okay.
Okay. Yes, I had a little problem.
Mhm. So may I now request Dr. Joita Dotto?
Invited
Ayuda,
speakers.
we cannot hear you. Ayuda.
Yeah.
Hello, may I continue?
Yeah, sure, please.
Good afternoon, the invited speakers, our guests, my colleagues, and my dear students. Currently, we are going through a pandemic situation due to COVID. Once again, I welcome you all to this webinar organized by RANAGHAT College. It is my privilege to introduce our next speaker, Dr. Somnath Bokshi. Dr. Bokshi is the Faculty of System and Synthetic Biology and Department of Information Engineering, Cambridge University, UK. He did his PhD from the University of Wisconsin-Madison and then moved to Harvard University for his postdoc. During his postdoc, he had developed a novel self-erasable fluorescence barcoding system, which enables harnessing the throughput for boosting multiplexing capabilities without any need for cloning and sequencing. Today, his title of lecture is Noise in Biochemical Reactions in Living Cells, Challenges and Opportunities. So with these few words, I would request Dr. Bokshi to deliver his lecture. Please, Dr. Bokshi.
Thank you very much. Let me quickly check if my sharing screen works well.
Yeah, please.
I don't seem to get the pop-up for, okay. Let's see.
I think you're having some problem with the connection.
Now it's okay.
Bokshi, is it okay?
Yeah. Now it's not. Yeah.
So can you see the screen now?
Yeah, we can see the screen, but your video is missing.
I can see my video at the bottom of the screen.
Yeah, now it's okay. Yeah.
Now it's okay? Sounds good? Okay. Okay, is it full screen and can you see my cursor?
Yeah.
Okay, all right.
Yeah.
All right, then thank you very much for the kind introduction, and thank you again for inviting me for this talk. So I was quite tensed because you can see from my introduction that I'm for like last several years I'm working in fields of biology. And when I saw that I had to present to chemistry students, I had a bit of a tension sort of event, and so I decided to sort of reformulate my talk in a way to sort of make it more available to students in chemistry. And when we look at biological reactions in sort of at the fundamental molecular level, there is, they definitely can be formulated with sort of the chemical reaction framework that we are more familiar with. And so that's what I've tried to do. I have tried to distill that aspect of our research. And I have picked some examples where we can sort of illustrate this sense with. And so whenever we look at biological reaction in a cell, one of the fundamental aspects that becomes very much apparent is that there is a lot of noise. And the noise here, we're sort of just referring to the usual sort of noise. What we mean by it is that whenever you're trying to look at a signal, there is a lot of, often there is a lot of irregular fluctuations. So similarly, if you're looking at cells and the cell is trying to express some protein, if we look at lots of cells, we see that different cells have different amount of protein. So there is a lot of noise in the expression level of that protein. And so that's the mystery that we will try to sort of understand throughout the talk today. But before I sort of unravel that mystery, I think I'll just present even the main clue to that, which is the fact that if you look at cells, and here is a cryo-electron microscope image of lots of small bacteria called E. coli, you see that if you consider these cells as our test tubes, they're really tiny test tubes, right? Because a single cell has this dimension of only like 2.5 micrometer in length. And so the volume of these test tubes are only 1 femtoliter. And so compare that in your mind with the volume of a normal test tube in our lab that is about of the order of milliliter. So there is several orders of magnitude difference between the two. And we can explore how that will sort of play into this heterogeneity throughout the talk. So I just thought I would just reveal this clue so you can, while I present, maybe students and all of us can try to see like ourselves, like how that might sort of contribute to the noise. Now, just to sort of give an outline of my talk so that you know what to expect. First, we will spend some time to define the process for which we will study the noise. Then we will go and define the system in which we will study this particular process. We'll then sort of explore the concept of cellular heterogeneity because it can be both from genetic and non-genetic. Then we'll explore the reasons underlying this sort of phenotypic heterogeneity, which is the main topic of this talk. And we'll then discuss some method development about how can we analyze such phenotypic heterogeneity. And we'll end the talk by a few examples about how.
Somnath, I'm just sorry to interrupt you. I think your slide in the below side there is a question. I mean, some shades are there, so slide is not visible properly. I mean, the whole full screen is not observable. So, and I request the participants also. So please mute. Please switch off your mobile. Either switch off your mobile or please in the mute mode because some noises are also coming.
Is it okay now or?
So could you please do it at the repeater, just exit and then share it 1 second, please.
Okay. How about now?
Yeah, now it's okay. Perfect.
Okay, you can see the entire screen. Okay.
Yeah.
So maybe I'll just repeat the outline once more. So first we will try to so maybe just go back to the title. My transition is not working though. Okay. So as you said, I don't know if this slide was clearly visible. That we're studying noise.
Now it's okay. Now it's okay.
Yeah. Okay. Studying the noises in the processes. So first thing we'll do is that we will define the process for which we will study the noise. Then we'll go and sort of define the system in which we will study these processes, and then explore the types of heterogeneity in cells, which is sort of reflecting this noise. And then eventually we'll also explore the reasons for it, like why there is so much noise in sort of biological process. And we'll do some method development with which we can actually analyze this kind of noises. And in the end, we will sort of end the talk by giving 2 examples where studying this kind of noise can be quite useful for us when we're analyzing biological phenomena. So coming to the points, what I decided to do is that I wanted to make the talk really basic. So I'm going to, as you know, background information at all. So it is mainly sort of structured for students. And so if there are researchers, I apologize to them for sometimes being too common. So we'll start by defining the process, and the process that we're going to study is gene expression. It's a very fundamental process, and we're clear with this that in cell, the gene expression happens in 2 steps. The genetic information stored in DNA that gets transcribed into this intermediate called ribosomal RNA, mRNA, and that gets translated into proteins. So in cell, sort of all these structural and functional work is actually done by the proteins, right? And so the type of function a protein has is encoded by the sequence of amino acid that it has. Okay, and this sequence of amino acid is encoded by the sequence of nucleic acids that is stored in DNA. So DNA is the information storage unit. Okay, so to give you some basics of the system is that when the first step of the gene expression is that from DNA, this enzyme called RNA polymerase makes RNA. This is a temporary intermediate, and they're both nucleic acids. You can see that the language hasn't changed about the information. So it is still in the language of nucleic acid in the DNA and in the nucleic acid in the RNA. So basically, you're just copying the message. So it's about like writing. That's why it's called transcribing. So it's just a transcription event. But when you go from nucleic acid, which is the RNA, to protein by this enzyme called ribosome,
you're actually changing the language. So you're going from nucleic acid language to amino acid language. So that's why this step is called the translation stage, right? And these are the two fundamental steps which we are going to study, okay, in this thing, in our sort of talk today. Now, let's define also the system. So the system that we're going to study is a bacteria cell. There are any cells we could have studied, but we picked this cell because it's simple and it's used as the model system for most microbial work. So there are a lot of sort of super resolution microscopy studies that we have done and other people have done, and also lots of high-electron microscope studies to know what's inside a bacteria cell like in E. coli. So with these we get very rich information, and therefore with those, David Goodsell has done this fantastic illustration that shows if you could cut open E. coli, what would you see? And you see these very colorful particles that are, these are these proteins, they're representing the proteins, but in the center you have this yellowish fiber, and that's the chromosomal DNA of the cell. And if we could actually sort of look at that, that yellow fiber and stretch it out, it will look like a big giant circle, okay? And different parts of that circle actually are the different genes from which we can express different proteins. The cell uses this particular gene to make this blue protein or this purple protein, just to illustrate here. And so there are lots of genes, but if we sort of have some simple assumptions or use our simple knowledge of the system, we can actually very quickly get a sense of how many genes there are. So for example, if we look at the number of base pairs in the DNA, we know that there is about 4.5 million base pairs, okay? And we also know that roughly a gene has a length of 1,000 base pairs. So with that, we can say that, okay, there are about 4,500 genes in the whole chromosome. So an E. coli cell should be expressing about 4,000 types of different proteins, right? So that we can tell just from basic knowledge of this system now. Okay. Now, the one thing I will also reveal is that even though a cell is supposed to express or can express 4,000 proteins, when we look at these cells at different conditions, we see that only there are like 1,000 or even less number of proteins are expressed. And this is the question we'll come back to. Like, why is the cell not expressing all the proteins that it can? Okay. But so far we have sort of established our system, E. coli, which can express 4,000 proteins. If we now look at any of these proteins and look at its amount, so here we have lots of cells, and in colors, sort of in a grayscale, we're plotting the amount of protein per cell. We see that different cells expresses very different amount of protein. Okay, and this is a fundamental experiment that was done by Michael Lewis's lab, and that was a very nice evidence for that there is sort of heterogeneous gene expression among the cells. The actual experiment was way more clever than the way I'm describing, but the essence is this: that different cells have different amount of protein expressed, and so there are clearly fluctuation gene expression in every cell. And so we can also establish the term phenotypic heterogeneity. As I mentioned earlier, that all these cells have the same chromosome. So the genetic sequence in all these cells are identical. So we'll call them to have the same genotype. But because they're expressing different amount of proteins, we will call that they have different phenotypes. So there is lots of phenotypic heterogeneity in this image. Okay. We have established that this system's gene expression is noisy. How can we quantify? How noisy is it? So to quantify the amount of noise, we use a term called coefficient of variation. Okay, so that's basically a ratio of the standard deviation of the expression over the mean, right? And the reason we scale this mean is pretty obvious, because the standard deviation can sort of scale with the mean. For example, take an example of like people's age distribution. If I told you that I know the age of some kid to be sort of an average of 3 years with a standard deviation of 3 years, you would see that I basically know nothing about the kid's age. So there's lots of variability in my understanding of what the age of the kid is. But if I told you that I know the age of an old person with an accuracy that he has age of 75 years, but with a standard deviation of 3 years, you know that I know his age pretty well, right? So therefore, this standard deviation of 3 in these two scenarios have very different sort of feeling for the variation. So if we scale them with the mean, so in our case, if we scale the standard deviation of the kid's age by the mean, we'll get a CB of 1. So that's a very large noise. And if we could scale the CB of the old person, 3/75, we'll get a 1/25. That's pretty low noise. So it's very good precision for us to know the age of that person. Therefore, that's what we do with the expression of proteins as well. So here in the green sort of curve, we have the data for expression of a particular protein in cell. And if we quantify the coefficient of variation, we see that the CV is around 0.5. That's a pretty large variation. And so the question is why there is so much variation. Okay. And to do that, we'll actually go back to the original, one of the last question I asked, which was if a cell has all these 4,000 genes, why is it only expressing only 1,000 of them or only 25% of them? That means that at a time, there's only a fraction of the genes are active. So to kind of explore that idea, we sort of go back to the concept of gene expression. And the simple structure of a gene is this, is that you have these genes from which you're making the mRNA and then eventually making the protein. To make the mRNA, the enzyme called RNA polymerase has to actually bind to this sort of upstream region of a gene called the chromosome. Right? So RNA polymerase diffuses and searches, binds to this region, and eventually starts to transcribe. But the binding affinity of an RNA polymerase is very tightly controlled by factors called transcription factors. So there are two types. There are transcription activators that can activate the gene expression, meaning that they can actually help an RNA polymerase binding. So in that way, if there is a transcription activator present and active, it can actually turn the gene on. The rest of the time, the gene could actually be off. Similarly, there are transcription repressors. Right? And so these repressors actually prevent the RNA polymerase to bind. So if they are present, the gene is generally off. Okay. So sense of what it means to have 25% of these genes actually active, it means that the combination of transcription activator and repressor at a particular condition keeps only a certain fraction of genes active. And the reason that is the case is because cells have to respond to a lot of environmental signals. And the way cells respond to environmental signals is that different signal triggers different transcription factors, and one transcription factor can control multiple different genes to be either activated or inactivated. Okay, so if it's an activator, it will activate genes. If it's a repressor, it will repress. And you need different set of genes for different tasks. For example, if you have lots of food, the cell will turn on happy genes. It will become very fat. It will grow really fast. If there is no food, the cell will actually turn on stress response genes. The cell will become really small. It will not grow at all, and so on. Similarly, if this environment is too hot, it will turn on heat shock genes. If it is too cold, it will turn on cold shock genes. So there are these kind of controls. But the essence of what I wanted to get across here is the fact that a gene has two states. It can be active or inactive. So with that, we can sort of have a bit more detailed picture of the central dogma, and just write an equation here, which is that a gene can sort of go back and forth between this inactive and active state. The transition is controlled by the level of transcription factors that regulate that. Once a gene is active, an RNA polymerase can actually make RNAs from those, right? This is the process of transcription. And then this RNA is very short-lived because it can be degraded by this enzyme called degradosome to nothingness. And then until it's degraded, a ribosome can bind to the RNA and make protein. Okay? So I hope that picture is that's very clear to us. So this is something we'll use throughout the talk. So this idea that genes can fluctuate between active and inactive states. When they're active, you can make a RNA. When the RNA is not degraded, a ribosome can make sort of proteins out of it. Now we'll actually use the sort of original clue that I gave, and this kind of ties back to some of the things that I was also saying, is that here things are not, we cannot treat things anymore in sort of the classical limit. And the problem is that the bacteria are really, really small, right? As I mentioned, that a bacteria, what is this annotation? So bacteria are very small, and their volume is only 1 femtoliter, right? So if you could measure the protein concentration in a bacteria, you get about 300 milligrams per milliliter. And we know roughly the size of the protein. If we calculate, we find that there is about 1 million proteins per cell. That's a lot of protein. But remember, I mentioned that there are 1,000 types of protein. And actually, in reality, there are few proteins that are expressed in really high amount. For most proteins, the copy number is actually really small, 0 to 100 copies for each protein. We are now actually looking at reactions that involve discrete amount of the reactants. And so even though we could have treated them with concentration, for example, you can see that if in a cell, if something has a concentration of 1 nanomolar, it means that there is only one copy number of that protein. And you can immediately see that concentration has no meaning anymore, because we cannot treat it as a continuous variable. This number can just go in this, like to 2 or to 0. So these are the things we learned about so far about this reaction network, that every player in this system is present in very low number, and their numbers are discrete. So we cannot treat them as continuous variables. And so what are the, sort of, let's get a sense of the numbers. So the transcription factors, the first step, they're present in only 0 to 10 copies number in cell. Very small copy number. Genes. So genes can be present, so active genes that are actually able to produce RNA are present in either 0, means that they're inactive, or 1. The number of RNA one can produce is also very low, 0 to 20 copies. The number of proteins that you make from an RNA is 0 to 100 copies. So we're dealing at a very low number region. Okay, and so what is the consequence of that? Consequence of that is that because any reactions in a cell will therefore include stochastic sort of a probabilistic collision between the reactants, the outcome of that reaction will be very noisy. Because often you will just find the partner that you interact with, you get an activation of the gene, often you won't, and the gene will just stay inactive, right? And so this probabilistic collision aspect is true for any chemical reactions, right? But the problem with cell is that because the number of players is so low, you actually get this much noise. In real chemical, like a test tube, the number of players is so massive that you cannot see. The time average looks like a nice continuous concentration. The fluctuations are unobservable in that scenario. So, and this is true for any level. So if we look at this kind of low copy number effects, and we take some reasonable approximation of the parameters inside a cell, we can actually simulate the behavior of these reaction networks. So, for example, transcription factor binding will make a gene fluctuate between the inactive and active states in a stochastic manner. So for example, here the red trace shows you that the gene goes to 1 and then comes back to 0 and keeps doing so for like a long time, and in a very erratic manner. And when the gene is activated, the RNA polymers can start to make proteins. So here's the state. You can see that, sorry, it can make the RNAs. And so the RNA amount goes up. Here I'm plotting RNA amounts. And then when the gene is inactivated, because there is no synthesis, the RNA amount just declines. And sometimes the activation is so brief, like these two events, that the RNA polymerase has no time to even make an RNA polymer. There are no synthesis in those times. So that's how you get very much fluctuation very high fluctuation in the levels of RNA. And when the RNA is present, the ribosomes will actually make the protein. So you can see that when the RNA is high, the protein amount goes high. But when the RNA disappears, there is synthesis in the protein, so the protein amount starts to decline. So the protein basically tracks the fluctuation in the RNA. That's why all these components in a cell will have a lot of fluctuation. And that is why there is so much variability in the cell. You can even from this simple simulation, you can see that the CV can be pretty high as 0.26. Here's the definition of the CV. So how can we sort of really analyze? So this is a more or less accurate simulation, but we need to look at real experiments. So what Michael Lewis did is that he kind of approximated the system in a way that he expected that it's following the ergodic hypothesis, which is that the system is homogeneous in space and time, and therefore you can actually look at the level of heterogeneity across the population and approximate the level of heterogeneity per time. So the fluctuation time series can be approximated by this. But you can see from just these images that the environment is not really homogeneous. Like this cell is surrounded by several other cells, whereas this cell is not so, right? And so there is definitely an inhomogeneous environment. And in an inhomogeneous environment, you cannot really look at the heterogeneity of gene expression and actually assign the entire noise to the fluctuation underlying that particular type of reaction. So the first thing to do is that we make sure that the environment is homogeneous. Okay. The second thing is that we'll also explore exactly how are they measuring this gene expression, and is that a reliable measurement? And if not, how can we make it more reliable? So the first thing we did is we devised a microfluidic device that actually takes care of this problem of spatiotemporal homogeneity that is required to study gene expression noise. This is a device called the mother machine, and I'll explain why that is so. So it has these very, very narrow trenches where only one single cell can grow side by side, right? And so we have these very narrow trenches and a single bacteria can sit in them, and it grows and then gets washed away by the media that's going through. And these bacteria are getting fed by the diffusion of the media that is flowing in the orthogonal channel. So you can keep the media flowing and you can keep the condition basically uniform throughout the entire time. So you have a temporal uniformity. And because we are keeping all these cells separate in these different trenches, we can make sure that there is also spatial homogeneity in the system. Okay, so this is the 3D architecture of the device. We have these very narrow trenches, 1 micron wide. A cell can sit like this, and then they grow and then divide and get washed away. So here's a movie of seeing single bacteria growing in the device. So this has really sort of revolutionized the sort of analysis of stochastic gene expression, because you can almost consider individual lines like a iteration of your code in simulation. So you have independent lineages growing in different ways. It has almost digitized this kind of experiments, right? And so if I look at one single cell and just look at its growth and division over time, if I plot them, I get this very nice exponential growth and then division when the cell becomes small again, and then exponential growth. And you can do it for sort of thousands of weeks and even like sort of hundreds of hours. And if I then look at the cell length over time and plot log scale, the slope of this growth actually tells me the growth rate itself. And when we did that, we can see that the distribution of growth rate over time is matching very nicely the distribution of growth rate across the space. So now we know that indeed this device is giving us spatiotemporal homogeneity that is needed to study stochastic gene expression. And the condition is fixed for really long time. So if you look at the interdivision rate, which is reflective of the health of the cell, we can see that that is fixed for really, really long time. So here we're looking at like 80 hours time. And bacteria grows only at a 20-minute doubling time. We can look at hundreds and hundreds of generations. And we can do so in very large number. So that aspect we can now address that, okay, we know now that we can study things in really, really uniform conditions. So any heterogeneity now we see in these cells can be ascribed to the heterogeneity of the underlying process. Now, how are we going to study the underlying process? So to do that, we use this protein called green fluorescent protein. These are very special type of proteins because if you excite them with a particular type of light, they will emit green fluorescence. Okay, and so what we can do is that if we take a gene where we have the promoter where the RNA polymerase binds and replace the gene with the green fluorescent protein, then we can look at the level of fluorescence in every cell, and we can get an approximation of the level of the protein. These are called transcription reporters. They report the level of transcription in each of the cells. You can quantify the noise in those. The advantage of this method is that the level is very specific. So you don't see anything beyond the itself, right? So it cannot read, there are no signal from all the other native proteins. That also means that there is no background, so you can actually have very low amount of light that you can use to look at this. And so this can, because you need very low amount of light, you can perform live cell measurement. So you can study dynamics. You can actually calculate this or estimate these fluctuation dynamics that you need to analyze this kind of system. Now, there's a problem in this kind of proteins. So the problem lies in this concept of maturation delay. From the time that a protein like this is produced until it actually gives the fluorescence, there is a lot of delay. And this delay comes from the fact that you have something called chromophore maturation. So in every protein, these are like these beta-branched proteins. Inside them, there are these few amino acids that come together and form this chromophore. And the chromophore does not fluoresce until there are these few steps, cyclization, dehydration, and oxidation, that makes them sort of come together and give enough resonance length to give this green fluorescence. You will see a signal until then. So that creates a lot of delay. And the delay is very problematic. So why is the delay problematic? So if you try to study a protein expression, let's say I'm trying to study the expression of this black sort of protein plotted in these black lines, it's fluctuating. And I have a reporter that is expressing the amount of this protein, but it has this maturation delay. You can see that my reporter is not able to keep up with the fluctuation of the protein because it has this delay, right? It smooths out the distribution. The problem also is exacerbated by the fact that the delay itself is also stochastic, because the reaction that I mentioned, that chromophore maturation, is also a stochastic process. And so therefore, you're going to get a distributed delay. You're not going to get a deterministic delay. So it will smooth out your actual fluctuation. And because of that, if you try to look at the distribution of the expression levels, you'll see that your reporter actually underestimates the noise than what is actually present in the system. So any measurement that people have used using these systems would have had a lot of problems. So how are you going to account for this? What we're going to do is that we're going to see, can we measure the true delay in a particular reporter that we're using? Develop a whole new assay to do. The second thing we will see is that can we now minimize the delay? Is there a way that we can? So how are we going to first measure the delay? So if we look at the maturation process, as a chemist, the first thing we can identify is that the rate determining step was actually the oxidation step. So it depended on oxidation. So we realized that if we could actually control the level of oxygen, we could actually study the kinetics of this process in life cycle. Okay? So that's just the simple gist of the idea. So how are we going to do that? So if we keep the cells growing in anaerobic condition, have no oxygen, then what's going to happen is that the cell will keep making proteins, but the proteins will not be able to mature, so they will stay dark. Okay, and any protein that was there present before will slowly become dark because they're just getting diluted. Eventually, you will have lots of cells that are basically packets of this fluorescent protein, but they're not able to mature. And then at some point, we'll just halt the growth and flush in oxygen, and we'll see how these proteins get mature in their characteristic timescale. So that's the assay. It's a very simple idea. And so here's one of the example data. You can see that here we have kept cells in anaerobic condition, and they're losing their signal very quickly. They're becoming darker because they're just not able to mature. The new proteins are dark. And then as soon as we turn on the signal, the oxygen, all the proteins get very bright and mature. We can actually study in individual cells the maturation kinetics. Okay. So if you look at any particular of these trenches, we can actually get a very nice time-lapse data of like how the cell lost signal, and then when we turn the oxygen, and how they recovered the signal. So here is YP. You can see these real fluorescent protein containing cells becoming dark and then very rapidly becoming bright, and then bleaching slowly at the end. But RAP, these red fluorescent proteins, cells are really dark, but then when you turn on oxygen, they slowly become brighter. And you can actually take every single cell of these and analyze the kinetics, and you can see that we get these beautiful curves from each of these cells about the expression level of each protein and how they mature over time. So YP is maturing really, really rapidly. RAP is taking a lot of time. And you get a very nice data. And you can simply use a sequential kinetics model that involves maturation and bleaching and feed all this data to extract really reliable numbers for the maturation time. So now we can actually have very nice measurements of exactly how much delay a reporter will give when we're trying to use it to record gene expression. Okay, now that we realize that we can do that, is there a way we can minimize it? The only way we can minimize the delay is that if we could find a protein that was actually very fast in maturing. Okay, so one thing we saw in the experiment is mentioned that individual traces have good enough quality of data that you can take one trench and extract a very nice maturation curve. So you don't need to use all these trenches, right? You just need one trench to get good enough data to quantify the maturation kinetics. So what we can do is that instead we can put different proteins in different trench and actually screen an entire library of fluorescent proteins to find a protein variant that is actually fast maturing. So that's what we did. We actually developed a microfluidic device where we can now look at 132,000 different trenches or cell lineages at a time, right? So here's the full montage of the device. There is a small crop showing you 230 such trench, and here's another crop showing you 4 of these trenches. And we can actually use all these single cells because we can segment all of them. And with this, what we can do is that we can now look at the 4 amino acids that flank the chromophore and make a full mutagenesis library. So because for every amino acid, you have one choice out of 20 amino acids, you can actually get 160,000 variants. And because some of those variants are actually dark, we can actually load the full library in our device and characterize every single one of them. Okay, so we can now actually look at an entire library of mutants in a single experiment and quantify their level of maturation. So that's really going to be a revolution for protein engineering because you can do time-lapse information. But once we identify the protein, let's say we found that this particular variant is right. How do you know which variant is that? How can you take it out and sequence it? For that, my colleague, Scott Luru, actually developed this technique where you can take an optical tweezer and take the cell out of the device and sends it out for sequencing. Right? After the measurements, we can take any cell out that we saw that was fast maturing, and we can keep it for sequencing afterwards. We can very quickly now find proteins that are very fast maturing. We did that, and so the idea is simple. We generate a mutation library in a flask where you have lots of different fluorescent protein variants. We load them in a mother machine, so individual trenches contain different types of fluorescent proteins. And then when we run our maturation assay, which is just controlling the oxygen levels, once we get the data, we identify the cell that is the fast maturing gradient. We take a optical tweezer, we take that, drag that cell out and deposit into the collection of, and grow it up to sequencing. With that, we have now a really fast folding sort of maturing protein that is maturing at 2-minute time. That's really nice for us to be able to track stochastic gene expression. So I'll take a short break here. So far we have developed methods that now we're confident that we can actually study gene expression noise quite reliably and also analyze them with theory. But the point is, why are we going to study this noise? So the fundamental reason is this: is that we are very much interested in understanding the source of noise. But then, as a systems biologist, my interest is also in how exactly the cell is suppressing noise that is harmful. We need to study noise for this. There are also scenarios where a cell can exploit the noise for its own benefit. And then I'm also a synthetic biology myself, so often I study this process to actually learn from the cell, to see if I know about the noise, can we design synthetic cells for better by suppressing the noise better? And similarly, can we exploit the noise to make more efficient synthetic cells? So today in the talk, I'll just give brief examples of these two cases. We'll give one example of how a cell can exploit the noise, and we'll give one example where how we actually can analyze the noise and make better synthetic cell by suppressing the noise itself. The example of cells exploiting noise deals with this concept of bacterial persistence. I think most of you are familiar with the idea of antibiotic resistance, which is that that in a population of cells, there are some mutants that just don't respond to the antibiotic. Right? So if you treat with antibiotic, every other cell will die, but these cells will, and then they will grow and take over the population. So that's the concept of genetic heterogeneity, right? Because you have different types of cells that have different types of genetic sequences. But even in a population of completely identical genetics, you can have rare cells who just happens to be in a noisy state where they are tolerant to the antibiotic. So when you treat cells with antibiotic, these particular cells will survive, but then when you sort of take the antibiotic out, they will recover the original distribution. They become identical. So, and the genetic sequences of all this population is actually still kept the same. So these are phenotypic heterogeneities. These are really the noisy sort of outliers that we just talked about. And they're much more difficult to study than antibiotic resistance because they're transient. You cannot accumulate them because you can never find them because they will appear and disappear. But the more harder problem is that they're very rare. Only about 1 in 10,000 cells will become persistent, right? So you have this very rare event happening, but that is also happening for a brief amount of time. You have to catch them at the right time, okay? And so because of these problems, it has been extremely difficult to understand the mechanism of the formation and the drug tolerance of these persister cells. And that has been really problematic because persister cells are one of the reasons why infections often always come back. You could imagine those commercials that we see or used to see where people will always say that our drugs or the soap will kill 99.99% of the bacteria because you cannot kill these other 0.001%, right? And so we need to really identify the reason for their occurrence and tolerance to be able to eliminate them. And so that's what we're trying to do. But how can we study them? So this is where the device mother machine comes handy because you have massive throughput. So you can study rare events like this kind of cells becoming persistent. And you can make sure that we have time-lapse images. So we can study this transient event that cells are fluctuating between the state. And you can see that when I treated with antibiotics, only this line of cells survived. Every other cell was killed immediately, right? So just repeating the movie again, here this cell enters into these persister states and these progenies. All the other cells are getting slowly killed by my antibiotic as we treat with them. While everything gets eliminated, these cells continue to grow and thrive. So they're the real persister in real time. And I think this is the first time people could actually see persister in real life. Okay. Now, how can we sort of know exactly why these persisters are rising? We did a lot of sort of experiments with those, and eventually what we found is that a cell becomes persister when it has very low amount of ATP. Okay? So here is a cell that has decently high amount of ATP. We use a particular signal, color map here. So if it is purple, it's low. So you can see that this particular cell grows, wakes up, and gets killed. But here, this purple cell becomes very slow, so doesn't get killed when there was a drug. This is the ampicillin drug, and then eventually grows up to just survive and proliferate. Okay? when we look at these ATP production enzymes using the venous protein that we just mentioned that we discovered, with which we can very reliably measure the true fluctuation in protein amounts, we classified our proteins in simple 3 classes, which is dim, meaning the low expression, medium expression, and then these are for bright expression. And we're looking at the proteins that are involved in the glycolysis pathway for producing ATP. And these enzymes, we see that for all these enzymes, whenever the enzyme amount is low, these are these dim situations, that's when the amount of persister formation is higher. So here we're plotting the probability of forming a persister. So you can see that the persister cells are arising from a very low level fluctuation of these proteins that causes them to make low ATP and making the cells persistent. So we can see now that the cells can actually exploit the noise in this protein level to stochastically enter a state that makes them tolerant to antibiotics. This is a very nice illustration of how stochasticity can be super useful for cells. We've recently submitted this paper, waiting to get out soon, but it's one of the first studies to actually test persister cells in real life and actually analyzing their mechanism of formation and tolerance. The last example I'll give is actually about a synthetic circuit. And so this is where we actually took this original circuit called repressor. So this has a very simple idea that you have 3 repressor proteins. So these are the transcription repressor protein I mentioned earlier. And they repress each other in a cyclic manner. And this is supposed to create an oscillation. This is something that almost started the field of synthetic biology in 1999. But in reality, this oscillator gave very good quality oscillation, and like most of the cells didn't even oscillate. So these are only the chosen few. But we have now sort of made noise analysis of this data, this circuit, and redesigned it. And with that, you can see every cell oscillates between these beautiful bright and dim states just autonomously. So every single cell is a robust oscillator itself. And if you look at the intensity profile, you see these very nice periodic oscillations that comes back up every 14 generation, right? So this is the intensity trace of one of these cells, okay? And if we these cells are so good oscillator that if you take one of the single bacteria that contains this oscillator and you plate it and then let the bacteria grow, you get these beautiful tree-ring-like patterns. Because every 40 generation, the cell starts to get this burst of high expression, and then they go down again. So we get these very nice rings, right? So the rings are very cool to see. We have this very nice oscillator, but how can we use it? Is there a purpose for doing so? So here's what we did. When we looked at the rings, this oscillator, we saw that the phase of the ring really depends on how long the cell has grown until you have started to grow them, right? And so if we plate a cell at 0th hour, we see that the center is bright. But if we wait 2 more hours, we see that the center starts to become darker, right? So if you look at the intensity pattern, and I can see that at different phase, the bacteria is at different times. So we can look at the phase of the ring, and we can actually know how long the bacteria has grown. Because if we spend 2 hours, the phase shifts like this. So here we plot the phase shift. Here we plot the elapsed number of generation until we have plated the cells, and we get a very nice linear correlation. And with this, we devised a very nice assay. We wanted to see, can we devise bacteria that can go inside our gut and actually tell us if we are having an inflammation. And that can be told by the quality of growth of the bacteria. We did this experiment with mice, where we can take the bacteria that has the oscillator, we feed this to mice, and then we record its phase before we feed it. And then when the bacteria comes out of the mice, we can then plate it again and actually look at the phase difference, and we know exactly how long the cells have grown in the mice gut. And quality of growth is a very nice indicator of inflammation, because we can run tests where we make the mice a bit sick. We get very nice sort of record of the growth heterogeneity. Okay. So with these examples, I'll stop my talk today. But before I finish, I'll just give the final takeaways that we can all try to remember. So the first thing we learned is that cells are very small. We learned cells are so small that concentration is quite meaningless. We have to treat things with numbers. So we have to treat things at discrete levels. We also learned that cells contain very low copy number of pairs that are involved in gene expression. Their copy number is always less than 100. And because of that, the fact that they have low copy numbers and that they undergo random collisions, we learned that gene expression is quite noisy. And that is the underlying reason why there is so much variability from cell to cell. Even cells with the same genetic sequence will have very much difference in their population. We also learned that we need to quantify gene expression. We need environments to be very homogeneous. and we also need very, very fast reporter to reliably track the dynamics of the fluctuation. So we can always measure anything, but it is very difficult to measure something very reliably so that you can actually do theory and actually compare with the experiment. So making a good experiment is extremely difficult. We also learned that cells can suppress or exploit this kind of gene expression noise for their own benefit. And finally, we learned that as synthetic biologists, we can learn from this principle, analyze the noise, and we can make very, very precise synthetic cells for different purposes to be used for clinical purpose or something else. With that, I would like to thank the people that were involved in the work. So most of this work that I presented, the experimental work, was actually done during my postdoc in Professor Johan Paulson's lab in Harvard Systems Biology. And these are my colleagues, Emmanuel, Charles, Sylvia, and Burak, who were the main collaborators that worked with me on these projects. Here is my current lab. I have my own lab now in the Department of Engineering in University of Cambridge. And I'm very fortunate to have three very bright students, Camilo, Georgios, and Charlie, and they have started to do PhD with me. And we're still continuing on the same tracks, more or less. And I think as the talk sort of give an image of, and hopefully in our future publication, we'll be able to see more of it. With that, I would like to thank the audience and the organizers to invite me, and I'll be happy to answer any questions that you may have. Thank you.
Yeah, thank you, Dr. Yeah, thank you very much. Thank you, Dr. Bokshi, for his nice lecture. And I think he will be happy to take questions from the audience. So, audience, please.
Sure. Should I keep the slides up?
Sorry?
Should I keep the presentations on, or should I stop sharing?
I think it's depend on the audience, but you can also
Yeah,
now
maybe I'll keep it. If they need to go back to any of the slides, maybe we can go back.
Yeah. So I can see from the chat section one of the question. I mean, right. Environmental factors control the transcription, so that if environmental factors changes continuously, then will it also affect the amino acid sequence every time in translate?
So yeah, so here what I basically just go back to this point more clearly. Yes. So here what we're saying is that what the environmental factors are actually affecting is the level of individual protein expression. So they only affect the actual amount of a protein, not the sequence of it. So there are, of course, environmental factor like in UV that can actually break a DNA and cause mutation. That will change the amino acid sequence. But in general, environmental factors only sort of regulate the relative amounts of proteins, not their sequences.
Okay, thank you. I think it's a question from Ankita Paul. I think she satisfied. I think she. The second one, is there any process to destroy the ATPs? Any process that will kill or destroy the ATPs that are formed again in the persisters that are formed after removing the antibiotics?
So actually, the story what we just is actually suggesting that it is the low ATP that makes a cell a persister. So cells need a lot of ATP. Sorry. Yeah. Yes. So actually, if a cell has low ATP, then it is becoming sort of a persister. So maybe if we want to eliminate persister cells, our goal should be to see that if we have a population of cells that have very low ATP, is there a way where we can externally actually make those cells have high? Like, can we induce ATP production so that they are now sort of more susceptible to the antibiotic? So the idea of persister is kind of like a sleeping cell. They're dormant, right? So if you have a war and you're sleeping at your home, most people that are sleeping at home, they're not vulnerable to the war. If you only get out, then you get vulnerable. It's like COVID, right? So you need to get out to be susceptible. So these cells are basically just sleeping away by keeping the ATP level so low. It's like our dormant states, so that the process that actually these antibiotic targets is not even taking place. So our task should be to somehow to make them wake up and be vulnerable to these antibiotics. I'm kind of like imagining your attempt to us to understand how can we kill the persistence.
Okay, so there is another question. I think I should move from this one. It's a question like, how do you generate the theoretical simulation?
Oh, so didn't try to put things very easy, but maybe let's go back here.
It's from KB.
Sure. So there's a particular algorithm called Gillespie algorithm that actually generates exact sort of simulation of this reaction network. The way we do that is that because like a particular state of the cell, like if you imagine this process happening in a cell, can have one reaction happening at a time. For example, let's say a gene can be activated or inactivated. Then that same active gene has a probability to become an RNA. The RNA has a probability to become degraded or become protein, right? And so what we do is that we actually calculate the rate of individual states by just knowing the numbers. Like if we put particular numbers on those equations, and then once we put the number of the actual number for the rate tells us the probability of that reaction happening. And it's an exponential dependence, but basically you can simply think that if a reaction has higher rate, it is more likely to happen, right? And so what we use then is we use the law of total probability. We actually then say that, okay, these are the total number of things that can happen in a particular time interval. Then out of these, which is more likely to happen? And so we basically do a coin toss kind of experiment in a simulation. And we choose like, okay, in this step, a gene gets to activate, or in this step, a protein gets to be made. And so using those kind of random number drawing, you can actually simulate these kind of random cases. But I think if you're like interested in more detail, I can, I think like looking at the Gillespie algorithm is something that will help a lot. And I think that I don't want to go too much detail into that here.
Okay, thank you. So Ankita Paul also posted a message. Thanks a lot for your clarification and very informative session. And the second one, I think this is the last question from the audience. Please tell me again, Bipasa Banerjee, sir, please tell me again, what is the transcriptional reporter and what is its role for measuring the amount of a protein?
Yes, that's a very good question. Really. So here, so one thing I didn't mention throughout the talk here is actually, or maybe if we go back to the slide I was at. So there, you can see that there are different fluctuations that are happening, right? There is the gene fluctuating between on and on stop state. The mRNA is fluctuating in different level, and the protein is also fluctuating. The one thing we can see from this kind of data is that the fluctuation that is that eventually contributes to the amount of the protein is actually at the level of the mRNA, right? So whenever we're trying to analyze the fluctuation levels in a protein, the main amount of fluctuation that it inherits is actually from the fluctuation in the mRNA. So most noise, so that could have been also put as one of the final takeaway, that most noise actually is in the transcription event, not in the transcription event. That's in general true. So therefore, we are interested in studying transcription, actually, when we are interested in studying stochastic. So that's why we designed these things called transcription report. The idea here is this, is that we want to know what is the stochastic expression level dependent on this particular promoter, because the promoter is what controls how often an RNA polymerase binds and make an RNA, right? And so that gives rise to this fluctuation. And so if we keep the promoter intact, but just replace the entire gene of the protein with a GFP, then we are no more keeping the sequence of the actual protein, but we keep all the architecture of this upstream promoter to know how the fluctuation of the gene could have contributed to the noise in the protein level. So that's why we are here just reporting the transcription, not translation. That's why we call them the transcription reporter. I hope that is clear. If not, definitely I can clarify more.
Yeah, I think now it's tea time, but we do have enough time, I guess, because we are almost in the virtual world. So there are 10-15 time. So if you any audience or participants would like to ask some questions to Dr. Goswami, then please go ahead. Because now it's tea time, so we are in tea time, and discussion can be possible, I guess. With a tea, discussion can happen. So there is one question. I don't know whether this question it's from audience. What is the noise in the topic? I mean, it's a kind of noise that you are describing in your presentation. It's a what kind of noise? I mean, the noise in the cell, noise in the protein, or a noise in the whole system, or noise in the process of the drug delivery. What kind of noisy that is in your topic? I mean, in system biology, noisy or noisy in the. So please, Dr. Buxi.
Yes, so I mean, yeah, so I mean, you can see that like in any process, sort of the way I sort of frame this problem, you could see that any process that will involve sort of low number of players and involve random collision between them to generate an outcome will be noisy. And so the only noise that we studied in this particular talk so far is the noise level in amount of proteins per cell. right? And so you can imagine that I have a particular signal that wants to make some kind of protein in a cell, and I want to see that how reliably is the cell using that signal to make that amount of protein. If there was no noise, every single cell will make the exact same amount of protein. But because there is a lot of noise in this protein production process, even with a very definite signal, every cell will have a very different amount of protein. So we're looking at the noise in the level of proteins per cell.
Okay. From Shapun Bishas, a question: what type of fluorescence probe you have used, and did you use any 2D gel?
Sorry, what's the last question?
What type of fluorescence probe you have used, and did you use any 2D gel?
Okay, so like we're definitely not using much of 2D gel because we are interested in the time lapse behavior. In 2D gel, you can quantify amount of protein, but you cannot look at it over the time. What we want to do is that we can actually, so here's the kind of movie I showed you, is that we are looking at cells living and growing over time. And so we want to track the expression level with sub-unit resolution over time. So we cannot do 2D gel, we can only do microscopy. And the probes we use are a special type of fluorescence protein. And the one that I mentioned that we have found be really maturing, which is something we used in our study. In one of these, yes, it's called a venous fluorescent protein. It has a very fast maturation time of 2.3 minutes. And so with that, most of the studies I mentioned about the ATP producing enzymes is actually done with this particular fluorescent protein.
Okay, very nice. And the other one is the what happened if sequence of amino acid changed? I mean, what will happen if the sequence of amino acid changes? The question is not clear,
Yes.
but it is.
Yes, I mean,
I guess it is in the
sure.
noise system.
Yeah, so you can that's in the regime of what we call a genetic heterogeneity, and in this case, there's like for example, like we're definitely thinking about sequence of amino acid being changed when we're talking about this fluorescent protein mutagenesis library, right? Like so, for example, we have this sequence of amino acid that makes this beta barrel and also makes the chromophore, and we know that if we change the sequence of the amino acid, it can either become bright or even go completely dark or mature faster. That is why we are exploring like these 160,000 variants. So these are all different sequences of amino acids to see the property of the protein. So sequence change in an amino acid most often relates to complete change in the property of that particular protein. In this case, we are interested in a protein that is fluorescing. Might be interested in a protein that has a structural role, like organizing into an multipolymer enzyme, or a protein might have a role as a transcription factor, which is activating the transcription of another gene. And so if you change the sequence of the transcription factor, it might get completely inactive. It will not be active as a transcription factor, or it can become super active. So all these probabilities are possible. So that's why you have to look at all the variants and find the ones that suit your purpose.
Okay, thank you, Dr. Baxi. And there is another question. I think this question from Kakuli Sharma. My question is: there any relation between phenotypic heterogeneity and pleiotrophy?
Entropy, I think definitely there is, right? Because so for that's more of an like evolutionary aspect. But if, for example, when we study bacterial aging, we see that certain things can make the like phenotypic heterogeneity where the cell's population pigment drops, and you can get antagonistic pleiotropy working. So this is a concept I think like maybe I'll refer to more detailed things like sort of literature to look at antagonistic pleiotropy and phenotypic heterogeneity, because I think for this talk we don't want to go too detailed because to explain pleiotropy will take some time.
Okay, so no more questions. So I thank you again, Dr. Somnath Boksi. And the last question from my part, it's from my student side. They are not daring to say you, but on behalf of them, I am telling you, it's a kind of question, kind of information that they want to know from you. That what are the criteria to enroll into the Cambridge University as a PhD scholar?
I think you have to, there is this application process portal called GAP. So I think it really depends on, so the thing with Cambridge is that you need to have a scholarship for the PhD. And so what happens is that Cambridge has this sort of a bipart system. It has university where all the classes take place, all the research take place, and it has these colleges where the students stay. Okay, and so the colleges are the ones that fund you. So I think the way to apply to a university, like any department, is that you have to figure out the corresponding colleges. And I think for India, there are lots of scholarships. For example, there are Monmohan Scholarship for St. John's College. There are several others. I can look up. I can, if interested, I might send Habibullah an email about the funding links where you can look for the possible funding sources that you can apply to. And so you have to apply to a department with that in mind, that a department can always offer you the position, but it will not be finalized until the college offers you the funding. And so one needs to sort of bring both of these things in place. Like you have to have good sort of CV, but at the same time, you have to make sure that you have applied to the proper colleges and funding schemes to get your scholarship.
Okay, so later I will contact with you in this regard if anything sort out or if anything will come. So there are a lot of feedback from you. Very interesting session. Thank you, sir, for this explanation. A wonderful presentation. So there are many more. So many more feedback for you. It's a light lecture. Finally, no more questions. So with this, from the audience, from the participant side, from Department of Chemistry, RANAGHAT College, would like to thank you very much.
Sure, thank you so much for inviting me.
Yeah.
I just is this presentation stop, right?
Yeah, you just exit
Yeah,
share.
I have stopped.
Yeah, registration right.
Yes. Okay.
Okay.
Thank you so much.
Yeah. Thanks. Thank you. So our next session actually, now it's a tea break session, right? 5:55 to 6:10. So I guess it's almost 6:03. So we can take leave in this time, or should I proceed for the next?
Now, will it be possible to check whether I can share my screen or not? Is it possible?
Yeah.
Because I'm doing with my handset.
Yeah, sure.
I don't
Please.
know if I can have any problem with that one. Did you put me as a presenter so far? I don't think.
Host admin, please make Dr. Please make Dr. Taposh Ghosh as a presenter.
Because I don't find. Sure.
Please make Dr. Taposh Ghosh as a presenter, please.
Doesn't matter. He is my father. No problem.
Okay, sir. Done.
Yeah. Now come the share content. Okay, that's fine. Share screen. Start now. Here. So can you see the screen now? Anything?
Yeah. It's
showing the starting slideshow. But the slideshow hasn't started yet, I guess.
Where is your video? Your video is missing. Yeah, right. Now it is okay. But we cannot see anything in the screen. Yeah, now it is okay. Yeah. It is okay. Perfect. So I think it's okay. Now it's okay. Tapos, it is okay now.
Okay, thank you. So maybe I just leave it here.
Yeah.
Stop sharing. When the session will start, I will do it again.
Okay, thank you. So moving forward, I think it's better to start this session because we do have only 3 or 4 minutes now from now. So may I now request my colleague Dr. Ranendu Shekhar Das to introduce our third session. This is the second session, our last speaker of this seminar, Dr. Taposh Ghosh. So I request Ranendu to introduce.
Thank you, Dr. Rahman. Can you hear me? Am I audible?
Yeah, you are very much audible.
Thank you, Dr. Rahman. For our next session, it's my pleasure to welcome Dr. Taposh Ghosh. He is the Assistant Professor, Department of Applied Sciences of Maulana Abul Kalam Azad University of Technology, West Bengal. And let me introduce him with a brief description about his academic career. He has an astounding academic career throughout his life, and he has obtained his MSc degree with organic specialization from University of Kolani in 2006. Then he accomplished his doctoral research works in synthetic organic chemistry under the supervision of Professor K.C. Majumdar, Department of Chemistry, University of Kolani in 2013. And he was a recipient of several prestigious postdoctoral fellowships, like in Scientific and Technological Research Council of Turkey during 2013, in Kobe Pharmaceutical University, Japan during 2014, and he was a recipient of renowned Alexander von Humboldt postdoctoral fellowship in Alexander von Humboldt Foundation, Germany in 2015. So after that, he has served for a brief period and professor in Department of Chemistry of Sri Chaitanya College, Havra, from 2017 to 2018. And finally, since 2018, he is serving as the assistant professor in Department of Natural Sciences, Macau, West Bengal. He already has published a number of research articles in reputed international journals, and his current research interests lie in diverse field of significance, like synthetic methodology and drug design, application of liquid crystals, carbon-carbon and carbon heteroatom bond formation, cascade reactions, synthesis of natural products and bioactive compounds, advanced organic photovoltaic materials, and others. And so with these brief details, I would like to, I would say, everybody please welcome Dr. Taposh Ghosh for this lecture. Thank you.
Thank you, Dr. Das, for your kind and generous words and introducing me. And it's a privilege, and I'm feeling very happy to be part of this one-day webinar organized by RANAGHAT College, the Chemistry Department, and the IQAC, the RANAGHAT College. And let me, with the permissions, let me share my screen. Okay.
Okay, sir, you are now presented.
Yeah, okay. Just allow me to share the screen. So is it visible?
Sir, please continue.
Okay, and I'm audible and visible both, I guess.
Yes, you are very much audible and visible. Not visible right now. Not visible.
But the video was on.
Yeah, your video streaming is off now. So please start your video first.
I think it's on, I guess.
No, your video is not. I mean, I request admin to put the Taposh Ghosh.
This was on, so I didn't do anything with that one. I just shared the screen. Is it any problem with the handset that when you do the screen sharing, your video goes off automatically?
No. I guess
Yes, from mobile, sir, video will not show. If you screen share.
Okay, then just please excuse me then, because I'm not happy with my laptop, so I opt the option of having the handset and go on with that one. So I hope you had no problem with that one.
Okay, go ahead, Dr. Ghosh.
Thank you. So as you see in the slide, that is a beautiful picture of Würzburg city, where I did my humble postdoctoral work at the University of Würzburg, and the title that have been already shared with you long back, and I have made a little change in terms of highlighting 4 words. In the beginning, you see the free space, and in the middle, you see the liquid crystals, because I want to emphasize these two, and want to grab the opportunity to go to the students, because I think the most of the participants here should be the undergrad students, which we don't get the opportunity to come close to them by far. And I hope the researchers and the faculties here, the senior faculties and the faculty, excuse me if I share little more slides that are very close to the students and easier for them to make the topic more understandable for them. So as I mentioned the 4 words, I first start with the liquid crystals and give you a little bit glimpse on the discovery of the liquid crystals, and then after the progress of that one. And in this sense, it was first discovered in 1888 by a botanist from Austria, Friedrich Renitzer. He was also a chemist as well, who observed 2 melting points in cholesterol benzoates. So before that, it was not found because mostly the crystallite have a single melting point. This is obvious for that one. But when he found these things, and when he heated the cholesterol benzoate, there was a heavy liquid before it melted liquid at 179 degrees centigrade. Later on in the next year, Otto Lehmann, a physicist, interestingly postulated this one as flüssig Kristalle in Deutsch, German, which means in liquid crystal in the English. And later on, Wallander, who is also a chemist, did investigate the systematically the rod-shaped molecules. I will come later into that one, mostly for next 35 years. And then for a few years, it was not any kind of research on this topic. And then in 1991, Pierre-Gilles de Gennes got a Nobel Prize in Physics for developing the methods developed for studying order phenomenon in simple systems, and that can be generalized to more complex forms of matter, in particular to liquid crystals and polymers. So I think the topic of liquid crystal is quite significant because Nobel Prize was awarded on that one. So this is getting importance day by day. And what was the hazy phase or hazy liquid that Renitzer observed? This was actually the 4th state of matter. And when I come to the next slide, I will it will be more general for everybody of us how this is applied in nowadays lifestyle. So coming to this slide, that it has to be the name of the liquid crystal. It has to reside in between the solids and the crystal, solids and the liquids, definitely. Now in the slide you can see over here that in gaseous phase or isotopic or liquid, whatever we say, we have a neither orientational long range order nor the positional long range order. So these things lack in these two things, these two phase of matters. Now coming to the crystalline state, these are very well orientational order and positional long range orders these have. Now in liquid crystals, what was there? It was the orientational long range order was there in liquid crystals, and there was no positional long range order in that case. As you can see over here in the middle picture, showing with the director angling that the molecules are aligned, having some orientational order, but there is no positional long range order in this kind of molecules. Now I would like to give a brief timeline in the history of liquid crystals applications, just from the beginning of the discovery, the current day, and what's awaiting beyond or in the future. So as you can see over here, from the beginning of 1888, you see a large gap until 1950 when the breakthrough discovery come with the in terms of
sorry to interrupt you, Dr. Ghosh. You can use your pen also on the screen, or you can use your hand or pen so that we can record this one.
Yeah, I think with the annotation I can do that.
Yeah.
I have the annotation. Where is this? Okay, no problem. Is it any problem if I say like that one? Because that may change the screen when I touch the mobile screen.
Okay, no issue.
No issue, I guess. Yes. Okay. So as you see, until 1950, there was not much research until the breakthrough in terms of cholesteric thermometer, because by that time we had 2 world wars in between. So everything stopped, specifically the research. So as for the liquid crystals, is the same thing, same fate. And thereafter, several things happened. The first prototype of LCD liquid crystal display was invented by George Hellmeyer, And then Martin Shad, a very renowned scientist who did the first twisted pneumatic LCDs. And then after a revolution was there in terms of devices that nowadays we see everywhere. I'm using the cell phone, you are having the laptops and everything, whatever you see, you are having a smartwatch or blah, blah, blah. There are so many things, and all the screens, either they have the LCD displays or LED displays and those kind of things. So until 2014, the discovery of liquid crystals has taken place enormously in large scale, in the industrial scales, in the industry of computers and laptops and camera, everything. Then came 2004, where the graphene was discovered, and with the help of that one, it's another revolution came. The first two-dimensional liquid crystals were reported that helped in the optoelectronic devices, in the photonics, in the material science, and then after it only grown up and up in terms of application. And in future, what awaiting for us is some wearable optoelectronic devices which we can wear as clothes or ornaments or something, which will have the liquid crystal input into that one, and also reconfigurable the meta structures and meta devices in near future. So before I go into details, that a glimpse of conventional mesogens. Now I should say mesogen term are for the compounds, the normal compounds that show the liquid crystallinity, they are known as mesogens. So all these molecules are showing liquid crystalline activity and they are mesogens, and the shapes are given over here. I just want to emphasize on the disc or discotic shape because this was invented in India by Professor Chandrasekhar. And so this is the Indian contribution to the big fraternity of the liquid crystalline society. And the things that are common in this kind of molecules are the shape anisotropy and the polarizability. These are very common in this kind of molecules. And the lateral chains are important. You can see over here, most of the molecules having different lengths of lateral chains, and that prevents the crystallization. Yeah, so this is so far shape related property and shape related invention so far. Now I want to share this slide, and this is for the sake of the students, that from the liquid to the crystal, how the mesophase or intermediate phases for the rod-like molecules, which is the simplest one, changes. Now you see in the top where we have the ionic, the isotopic part, where the molecules don't have any orientational or positional long-range orders that can transform to the crystals, and in between it was the normal situation that can transform the crystal by cooling. And if the cooling is done slow, it can go to have the nematic phase, which have a very minimal amount of orientational order. The nematic word came from the Greek word nemesis, and this is known as the thread. Like threads, the molecules are oriented in this way. After cooling, this gets a little more oriented, and a layer structure was obtained first time with the one-dimensional, although having some orientational and positional order as well with a director. Then this can change again in terms of tilting the angle, and then we have the symmetric C phase, which gradually form the more ordered and positional ordered crystalline things. Now here come the free space or intrinsic void space. That is the beginning of my work in Würzburg. We started with that one. This is the concept of the lab to work on these things. In last 50 years almost, the aim of the was it an echo or something? Yeah. Am I audible? Hello? Hello?
Yeah, you are very much audible. Go ahead.
Okay. Thank you. So in last 50 years, the molecular material scientist has been directed towards the generation of the space, and this is for the uptake of the guest molecules, the macrocycles or cryptands, we can say, or the porous networks, which is very much common in nowadays, the MOF and COF. This is the hot topic of research nowadays. And because of the significance and of the implementation of this kind of materials in sensing, separation, catalysis, drug delivery, gas storage, and so very many things. Now in the picture you can see over here in the left hand side, in the liquid crystal phases, in the nematic, columnar or lamellar, or in the upper one, the porous liquids with molecules that incorporate cavities. Now the shape persistent scaffold is maintained with the blue color, and the cavities are shown with the red color. Yeah? These cavities are compensated in presence of the aliphatic chains mostly, and which may fill the space. And for the lamellar case, you can see over here that the nanosegregation for the columnar and lamellar phases occur, where it directs that the chains are going away from the cavity, so they don't come into the cavity, so they can have a nanosegregation in the mesophases. In the right hand side, I will spend a couple of slides on that one to show you the different molecular structures and the current research that is going on in this very topic of the intrinsic voids filling, and these are persistent mesogen and the intrinsic voids. So let me come into that one. This slide may seem a little bit more, what should I say, gathering or something, but I don't have the option to put into that one because I don't want to increase one more slide. Here in the top left corner you see the symmetric A phase, or the molecules that are known as swallow-tailed phasmitic calamitics. Now here the free space of the void, you can see with the red scratches, the parallel scratches over here, which can be compensated in the symmetric C. You see the middle picture of the left hand top corner left picture, that has been compensated in symmetric C and also in the nematic phases just by the molecular designing of those kind of molecules. So we can compensate by the design of the molecule, the void. This is one example for that one. The various groups have applied strong electron acceptors. You can see the green plate over here, that is the trinitrofluorinone compound, which is a very good electron acceptor, and they want to put that in between and create some host-guest interaction, and at the same time virtual voids of different sizes. The stronger interaction between the aromatic building blocks within the field symmetric A phase can even produce very rare Macmillan phase or biaxial symmetric A phases, because this can happen because the rotation about the long molecular axis will be prevented in that case. Just coming to the right hand picture in the right hand corner in the bottom, that shows the crown gear wheel compounds providing free space. Now you can see the compound in the right hand part of compound 8 and 9. I hope you can see if you enlarge the screen. That compound having the red part is the free space in the compound, which can be filled up by the triphenylene compound, which is shown as green, and you can see the combination 1:1 mixture of 8 and 9 with 7 comes up, gives a very much compensation of the free space, giving considerable columnar mesophase over a long range by means of so-called complementary polyphonic interactions. Next comes the left, bottom left slide, part of the slide, which shows the first compound of that one, the top one, shows a shows the molecule, the bowl-shaped compound cycloveratrylene, which is very highly ordered columnar structure. I think we can correlate this one very much with the bowls that we use in the household device as a household device every day. And if we put bowl one by one, we can have a column, and we see that the bottom of one bowl is compensating the space of another bowl. And by that way, if we stack together all several bowls, we will have a column. Now this is by internal compensation of this thing. Now if we can have this cycloveratrylene molecule and put one fullerene in between, the second picture you can see over here, that means filling by fullerene the free space, we will generate a super mesogen having a cubic liquid crystal phase. Now cubic liquid crystal phase shows very much significant role in nowadays, for there are several markets from optical fibers and electronics getting a whole market for the cubic phase. These are another structures with incommensurate building blocks, and in all the cases the space is on demand. I would like to spend some view on the top left with the shuttlecock molecules, because it's very interesting to say that the first pictures you see with the shuttlecock having some red part over there, the intrinsic void. In that case, shuttlecocks, they interact or compensate the void in a head to tail fashion. Now this can be changed with the molecular in some putting some functional group as methyl group. You see in the right hand part at the with the compound 20 that the methyl group when comes, it reduces the cone, and with the smaller cone containing a sterically interacting with the incoming another fullerene groups, and that results in segregated fullerenes. And in the right hand side with only you can see the lamellar structures. There is no head to tail filling of the space, only the lamellar structure. Now coming in the bottom part, I will not go into the right hand part. This is the typical macrocycles, which are the prototypes of in every time you synthesize a macrocycle, you will inherently you will synthesize some void in between in the middle of a macrocycle, definitively. Now in the later part, the tubular form, the three-dimensional tubular form, when for the macrocycles, the first molecules were synthesized by Nierengarten, where 1,6-dicyano-benzene was put in between that molecular structure, and the last one, the 26, was discovered by Fraser Stoddard. The first speaker today already mentioned that in 2016 he got the Nobel Prize for molecular machines, and he was the one who invented the rotexanes, and these are the liquid crystalline rotexanes that Stuart et al. Synthesized, and they started synthesizing the rotexanes from 1991. Now coming to our work, what was the challenge thrown to me? What I want to take as the strategy for filling up the space. Now being the synthetic organist, I opt to take the covalent attachment via a spacer to the right of the arm. That is the right hand part of the picture. You can see that fills the space. Now here, is it possible to see the pen or something on the screen? Yeah, I think it's visible, right?
Yeah, it's visible.
Yeah, okay. So here the first compound, the compound 1, this was synthesized before I reached the lab, the star-shaped molecule with 3-arm star, and that shows a helical packing in the molecule. Now the challenge was to fit the void in the 3-arm star. Now, as I said that I opt to synthesize it by covalent binding, and we choose fullerene as the filler or the guest molecules because it's very well known as an acceptor, electron acceptor. So we want to have an electron donor acceptor material, and we want to have the separation in charge into that one so that we can use that molecule, or that molecule can be can show the potentiality of being organic photovoltaic materials. So this was the thought, and then we designed the compound, and we see in terms of the liquid crystal nature, you see over here, it was 206 degree to the isotopic phase, and that transformed the same compound, the parent compound, only having a fullerene attached over one of the arm, filling 1/3 of the void, and that gives us almost 75 degrees stabilization in the liquid crystal phase. So this was very joyful for us, and we was very happy with that result. And in the later part, in the lower part, you see over here, this is the molecular modeling for this one cell. You can see over here how the shape amplifiers the fullerene molecules are forming the triple helical structures and filling the unit cells. Then in part of this result, we want to make the variation in the spatial length of the fullerene so that we can reach the fullerene to the periphery as well. And I mean, we want to have the fullerene over here, just beyond the head group in the molecular architecture. So we increase the number of fullerene spacers and also increases the oligophenylene spacers in the arms. And we had the result over here where we get the 360 helices and the 3D networks by the fullerene. I will come into detail of that work. Sorry. Oops. So here is, sorry, names of the route for the fluorine stars. You can see over here, I guess. So here the target compounds were synthesized by a convergence route based on Arbuzov reaction and the Wittig-Horner reaction that was mainly used for preparing the E double bonds, so that the unsaturation and the electron transfer get easier. And in the final stage, in the blue color in the product, in showing highlighted in the green part, you can see over here, and that value shifted from 2.3 around ppm or 2.90 in case of the shorter star, and for the methyl ester to 2.7 and around 2.3 or 2.3. So this is a huge shift in terms of the methylene protons. So these are very significant that the fluorine was attached to one of the arms. And in the right hand part, where figure 2, the signals are of the target compounds for the inner aromatic, the olefinic, and also for the outer olefinic protons, and they are clearly separated and highlighted in the different colors, with magenta colors, the orange and the green and the deep green colors. And the direct electronic effects were more prominent with the alcohol group, shifting adjacent hydrogens in the upfield directions, whereas the outer olefinic or outer aromatic protons of these precursors were not that much affected. Now this can be explained in presence of the magnetic anisotropy effect of the fluorine, which was just over these protons. So the interaction between the fluorine protons with the protons of this part of the molecule, that causes this kind of shift. So here you have the figure 3. This is for the compounds with the longer spacers. Now here we want to show that how fluorine was interacting mostly with the shorter spacers. You can see in the extreme left compound in figure 3. And then after the fluorine with increasing spacer lengths going in the periphery and having very less impact of the fluorine protons on the olefin aromatic, the outer olefinic and the outer aromatic protons. Yeah, so this is a representation to realize that, or in support of the 1H NMR data. That shows the optical mixtures that we get for compound S1, S1F2, S2F8, and S2F14. These are the star molecules, and everyone showing the columnar hexagonal phase, mesophase, that all the molecules are liquid crystalline in nature. And we have in support the X-ray diffraction of pattern for compounds, all the final compounds here, where we can get in picture F that for the target star molecules having the larger spacers for S2F8 and S2F14, we can very prominently detect the 0, 1, 1, 100, 110 and 200 peaks. However, for the shorter things, we only getting the 100 peaks as the predominant peak. Now, this is very important one to realize the figure 6a in the left hand side. You can see over here that reveals that fluorine must have to have a defined position with the mesogenic structures. This is very important because in the X-ray results, they present only the diffuse reflections that corresponds to the 3D structures and point to the low correlation length along the columns when the fluorine are stacking in terms of considering that sense. The ideal radius of the helical packing that was calculated for the larger mesogens or the larger stars are larger than the experimental columnar diameter. Now, the optimization of the nanosegregation of the fluorine that from the arm oligophenylene vinylene and the aliphatic chains and the space filling of the intrinsic void, these rationalize the formation of the liquid crystalline nanostructures within the molecular architecture. So this was very important for us to realize or understand how the fluorines are oriented before we go to the material studio and have the figure 6b, where it highlights the structural models for the larger stars. And this model was geometry optimized until we get very strong negative van der Waals in interaction value and electrostatic intermolecular interactions. And you can see over here in column in the top part or in the bottom part, this is for two different star molecules, that the two unit cells are filled by two different columns A and B, in which the fullerenes are organized in the triple helical structure. And you can see where the yellow, with the yellow arrow, you can see over here that the three-dimensional interwoven network of fullerenes, with one column to the adjacent column where it matches, the same color matches of the another column. And also between the same type of columns, the AA and BB type of columns, the fullerene helices also interact. And this model that reveals that the nanosegregation at the periphery of the columns and intersects with the neighboring columns to form a three-dimensional helical assembled fullerene structures. So this was very tedious job to have that one until we get the negative, strong negative van der Waals interaction value. So it's a month of 2 months job to get one picture of that one, to have a better understanding of the molecular architecture of that thing. Here in the lower part in the table, you can see over here, this shows the polarizing optical microscopy data, that the picture I have shown before, that showing the columnar hexagonal mesophases and all parameters from the XRD. So I will not go into the details. In my second work, we have the target to increase the core size from benzene, because so far we were limited to the benzene core. Now we wanted to have that we changed with porphyrin. Now this has two reasons prominently, because we want to make a more electron donor acceptor material, because porphyrin was acting as very known to have acting as electron donor, and the fullerenes were the acceptors. But this was our target. So far we couldn't reach that. But in the preliminary sections, we wanted to also have the increase the size, and in the meso positions where porphyrins were substituted, we can have more number of void spaces, and the larger voids which can be filled up by the arms and also the aliphatic chains. So this is the work, the shape persistent porphyrin star with the intrinsic void space. Now these are the star molecules that have been synthesized. You can see over here the 5 molecules where you can see that the thiophene and oligothiophenes and benzothiophene, those are connected in different arms, and we can have the star molecules over here. Now I will quickly go through the building blocks. You see over here the target compounds here. These are the building blocks, and the target compounds have been synthesized in a convergence strategy as well, using more stable and suitable functionalized porphyrin cores 5, 6, and 7, and also that with the common reactions like Suzuki coupling and esterifications and the Wittig-Horner coupling and Arbuzov reactions. These are the known reactions which have been implemented to prepare the starting materials and the arms, the building arms, and then we connected that thing with the core molecule to have our target star molecules. Now this is the thermotropic property study for the star molecules. See the polarized optical microscope images for the liquid crystal phases of the star mesogens 1 to 4, that the 4 star mesogens were formed. One have 1A and 1B structures, that's 5 molecules, and A to E, the first row showing the structure of compound 1B, the phases of 1B, and first A was the sheared amorphous phase. That's why it's showing the black color of that one. It was sheared, and B showing the birefringent soft crystal of material. Then we have the droplet structure when we put a droplet in between 2 glass slides and then rotate that the upper side by 45 degree. We have a picture as D, and also we use the lambda compensator. The yellow arrow indicate the direction of the planar growth of the columns. Also, figure 8 shows the model for the planar and homeotropic domains of the plates in from C to E, that C, D, E that we have for compound 1B. This is the molecular model for this one, how this can be, the results can be explained. Now for the G and H, this shows the texture of compound 2 with the homeotropic domains as highlighted with the white arrow you can see over here. And for compound 3, it was I and J and K, those pictures. and I and J are the pseudo-focal connected structures, very common for the hexagonal columnar mesophase, where the molecules are packed in a columnar style at different temperature you see over here. And picture L is for compound 4, showing also the hexagonal columnar mesophase. So this is the X-ray scattering for the molecules patterns, and from here we see that all the molecules showing similar kind of the indexation values with the 1, 0, 1, 1, 2, 1, and also in the wide angle when going to the 10 to 27 degree 2 theta value in the meridian, that shows the soft crystalline or columnar phases for 3 and 4 as well. Now here comes the table for the DSC and XRD data table. I can talk about later if someone have any query about that one, or you can go to publication as well. No issue with that thing. And I had to summarize this somewhere, so I put this slide up for that thing. And now come the geometry optimized structure for this one. This is very important to understand because this gives a very good highlight, and this and the next slide gives a very good highlight how the molecular orientation and how our claim to have filling of the space worked. Now here, in order to understand the actual spatial orientation, force field geometry optimization and were performed, and with all the stars, and DFT calculations were done for 1B and 4, compound 1B and 4 for them. And the figure highlights the force field optimized geometry. And except from right hand side, you see for the zinc porphyrin that the flat zinc porphyrin core having an out of plane turned phenyl mix, and whereas for 1A and 1B, the compass 2 geometry optimization show that these are the saddle conformers, and the saddle conformers they are the porphyrins and all planar structure for them. This is very obvious for that thing. And these results may be attributed among the others that to the smaller torsional angles around the 62 degree between the porphyrin and the conjugate oligotherapine arms in compound 1B, because the compound 1B and compound 4, these are having some different in geometry. So the reason can be the torsional angle, whereas in compound 4, the stronger out of plane turned phenyl rings, because that don't have any the structure, that is around 70 degrees. So that explains the geometry optimization for these two molecules. So coming to the molecular modeling of the structures, here the models of the soft crystal phase of 4, compound 4, A, B, and C. These represent that one, and the columnar LC phase for compound 1B with the figure of D. Now, A shows the schematic representation of a dimer of 2 mesogens that compensate the intrinsic free space and form the orthorhombic cell with the helical columnar stacking in the dimers. Without visualization of the aliphatic chains, we have removed that part. So it's only the molecular structure over here. You can see the 4-arm stars, how they interwoven into one another in the structures, and we have that's why it's one is yellow and the other one is green, shown to have the better visualization. Now the structure B, having the top view of 4 cells with aliphatic chains, the dimer is complete and interdigitation of the chains, but no entering of the core. You can see the chains over here. I'm having some background noise, I guess.
Please use your headphone. Yeah, you please use your headphone, Dr. Taposh Ghosh.
I'm talking from
speaker and
so I think the noise is not now.
Yeah.
Maybe I can. So in compound B, or the figure B, rather say figure B, that we see that the aliphatic chain didn't interact with the helical structures that remain in the outside of the unit cells mostly, and this is figure C is the side view without the chains. So we have omitted the chains, so has to have better view of the inter-oven interaction of the molecules in the unit cells. And figure D shows the model of compound 1B in its hexagonal columnar phase and helical packing structures, which is quite analogous to figure 4. Now, in summary, I would conclude that we have the intrinsic free space that affords both 3D network is concerned, and the packing and the space.
আমি ভাল লাগে না এত ভালো ভালো কিছু শোনার পর তোমাদের এই অবস্থা আমার মানে কথা আসবে এখান থেকে কিচ্ছু করবে না তুমি
Yeah, someone please mute your mobile or I don't know where from this sound come. Yeah, please go ahead, Dr. Tapos. I think sounds come from the other side. I mean some participants. Yeah, participant, please, I request you to please mute your audio, please.
So actually, voice background noise coming from speaker end. All participants are muted.
Okay, no, I don't. Okay. Go ahead.
Please continue, sir. Tapos, sir.
Okay, thank you. So, as I was saying, the intrinsic free space that afford the star molecules a tight helical packing to optimize the nanosegregation of the fullerenes into the molecular architecture, and therefore they are filling the vacant space. I am talking about the C60 helices and the 3D network. The first work that I discussed. Although the smaller fulleropyridine mismatch between the that prevents the alignment in the molecular in the columnar phase, and for the larger ones with bigger cavities, fullerene fits exactly, and an extraordinary spacer controlled self-assembly of the fullerenes was observed along the column, and that can lead the fullerene interwoven 3D networks with tight the oligophenylene arms in the center of the column. Yeah, so this was from the fullerene triple helical structures, and from the porphyrin star mesogens based on asymmetrically meso-substituted at the core.
I think it's a disturbance from the participants. Some participants' voices are not muted. I can see from this screen. I can see from the live screen. I don't want. I don't want to put his or her name, but please mute your audio.
Okay, sir. I also mute all button. Okay.
Yeah, please.
No. Me, I have to talk a little bit. Joke apart.
Continue, sir.
So for the porphyrin star mesogens, stars, zinc porphyrin core or choice of core, and number of conjugate thinyl and that phase in all.
Sir, please my headphone ta thik kore dhorun.
I think it might. So far.
Subhojit Haldar, please mute your audio. Mr. Subhojit Haldar or Doctor, I don't know. Please mute your audio. Yeah, Dr. Tapus, go ahead, please.
Okay. So the formation of columnar liquid crystals in the porphyrin stars is extremely sensitive to the conjugated and not because and all the it's very good for us that all the transition temperatures are below 200 degrees centigrade, and because of the out of plane rotation of the aromatic units. And now these findings with the space filling models packed in a helical columnar array, and this gives us the promising class of materials, these porphyrin stars, to go for further applications and seek an advantageous application for the transistors and the photovoltaic devices, and also for the antenna systems in the liquid with the liquid crystalline behavior. Now comes the very important slide, maybe the most important one, the acknowledgement part. So I want to acknowledge the Alexander von Humboldt Foundation and the University of Würzburg for giving me the opportunity to carry out my postdoctoral work over there, and AVH for giving me the prestigious fellowship, and my host for the fellowship, Matthias. I want to thank him as well for guiding and annoying so very many times for having better results. But at the end of the day, we had good results and we published that one. That's important. Also, Marcus, Moritz, Martin, and Lisa for contributing the works that I have presented here, and working together. It was pleasure for me. This is a group picture here when we go to the lab trip. And also, I want to thank Maulana Abul Kalam Azad University of Technology, Makout, West Bengal, for giving me the opportunity to pursue my research work further here, giving me the lab space and working atmosphere. And now we have the MSc Applied Chemistry students, so I hope we will be doing some research that I have shown over here, further extension for these things. And thank you for your kind attention.
Thank you, Dr. Tapas Ghosh, for your very nice and enthusiastic and very good lecture for the students and for the researcher. And I hope all the participants enjoy your lecture throughout the evening. So the session is open for discussion. May I request the audience and participants, please feel free to ask your questions or doubts if you have any. Please go ahead. We have finished all three sessions. We have finished all three lectures. So regarding your liquid crystals, this organic synthesis or the liquid crystal material, what you have, if you have any question, then ask. I do have a question. Someone posted in the chat section. Ankita Paul, will it? So it is a question from Ankita Paul to Dr. Tapas Ghosh. So how? Where is the question? So what are the? Will it affect the fullerene to bind if at the ending we have carboxylic group instead of ester?
No, we have bound the fullerene by the carboxylic acid group because we have to form the ester formation. So the methyl ester we have to take, and I have shown only for the comparison with the NMR data, because with the methyl proton you can have because with the carboxylic acid group you don't have the carboxylic acid group in the NMR. In the fullerene NMR, you see in the fullerene NMR, this is so very many peaks over there. So it was a hard job to identify the proton over here, and definitely we have made the ester bond formation with an alcohol functionality in the center, in the core, and with the carboxylic acid functionality in the fullerene arm. And then we bring that together and form the ester. So we have to use the convergent way, because the other way around giving us side products, and that were dominant. So the yields were very less in that case.
I think the second one, it's from Mr. Just a minute, please. Second one, yeah. Second one from Shayoni Chanda. Sir, what are the common characteristics? Where is the question? What are the common characteristics of the materials? What are the common characteristics of the materials which show liquid crystal phenomenon?
Well, it's difficult to understand the question because the common characteristic there is the materials are liquid crystalline. So these are common there, and it depends on the structures. If these are having similar kind of structures, so it may give similar kind of phase behavior. Like if these are rod-shaped molecules, so that will give pneumatic, smectic A, C, smectic H, G, those smectic phases which have the 1D layered structure. Now, if it goes to the discotic or columnar structures, then definitively this is the columnar mesophases. That can be hexagonal, orthorhombic, cubic, different kind of. So, and in terms of the characteristics, or I think she was trying to have the application of different types of liquid crystal. I think she wanted to know that.
No, the question is something like that. How can you say that when you prepare a molecule, or something like that, or a device, then how can you say that this is a liquid crystal, something like that? Or
if it's so, then I have the answer that you cannot say until you put that, because having the personal experience, I have maybe 50 or 60 sites that gone in vain. That's a solid only. So that's having only melting point used for me by that time. So until you put that under the microscope, you don't know whether the molecule is liquid crystalline or not, because before that, with the NMR and everything, it's a simple solid compound. Mostly.
So a very similar question: is there any method without any sophisticated instrument? Can you identify a liquid crystal material?
In terms of NMR spectroscopy or something, it's very difficult, because all are as usual as the solid substances that we do in the normal organic chemistry, in the methodology part. So unless you go for checking the thermotropic properties, because I said in the first slide that Renitzer had the 2 melting points in the cholesterol benzoates, only then he knew that this is something different from solid. Right. So until and unless maybe you check the melting point, and if you see that thing, then it's the only option. So you have to check some thermotropic properties.
So is there any use of a liquid crystal material that help in the drug delivery system? It's a question from Susrut Subham Srivastava. How can a liquid crystal helps in drug delivery?
Well, that's a very good question. I think these are the kind of hot cake in the research now. People are using the liquid crystal materials because this is in the drug delivery sense. You are trying to see what your drug has delivered or not. So in that sense, that when you inject a drug to a human being or something else, the drug is reached the target or not. This part liquid crystal can help you, because it can have the fluorescence character as well. So liquid crystals are, most of the liquid crystals show very good fluorescence characters. So in terms of that photophysical property, we can use the liquid crystal in the, I mean, drug design, not in the designing, but to see whether the drug has reached the target or not.
Okay. Thanks. And the last one, I guess there is no other question. This is the last but not the least. So it will be nice for the other audience also if you can clarify this one. How can I compute rotational energy levels for C60 and C70 fluorine molecules using Gaussian?
Oh, I think if Arnav is here, he can say a little more, because this is typically not my cup of tea. It's going to
actually Arnav, now he is in the meeting now. So in Cambridge, I think he is in the meeting now. Sorry, IIT Kanpur. So maybe Arnav can explain this one. What kind of materials are using to dope fluorine C60? This is another question.
fluorine, I think this is not very relevant to my research work, because I was not doping the fluorine. It's only the functionalization of the fluorine. In terms of that, we did only the functionalization terms, and being the synthetic organic chemist, we only I only prefer to do the functionalization, and then after having some molecules that show the liquid crystalline.
Yeah, this is a question from Dr. Urjit Mondol. Which free modeling software allows me to create a model of fluorine-like structure? Is there any free modeling software?
Free modeling, that's tough question, but Material Studio, I think we have 2,000 euro contract for 2 years. Maybe it's expensive. I don't have the idea of this software.
Now from Dr. Arijit Mondol, another question for Dr. Tapus Ghosh. Is possible to use carbonamide reaction for carboxylated fluorine C60 particles with synthetic peptides? Is that possible to use carbonamide reaction for carboxylated fluorine 60 particles with synthetic peptide?
Yes, I think I did that one specifically in the lab, but a colleague of mine, maybe I'm sharing her work little bit, because she was doing that thing of attaching the fluorine in the carbonamide linkage with that point of view with the synthetic peptides. So I think this is possible. There is nothing not to be possible there.
I mean, this nature of work is going on, right?
Yeah, so I cannot I say much about that one, but the only to say that is in the lyotropic liquid crystal phase, that is in the solution phase. So this is not in the thermotropic liquid crystalline synthesis. This was the lyotropic one, the other version.
So I think this will satisfy Dr. Mondal. So I guess there is no other questions. So thank you, Dr. Tapas Ghosh, for your nice and valuable and very interesting lecture. Thank you once again, and
thank
you very much for this session.
That you have invited, and I can contribute something, and if I can teach to the students, that will give me more happiness.
So we are almost at the end of this seminar session. So could you please, Doctor, I mean the host admin, please make me presenter, please.
Your name, please.
My name is presenter means if someone can, I think the participant can see in the screen. I mean HR, you can see Habibur Rahman. Not the presenter. I will not present anything. I just want to say something. I just want to say the vote of thanks. I have to say something at the end of the seminar,
Yes.
so that everybody can follow.
Your presenter.
And this is the last one. I just want to share the thoughts of this seminar. So I want to hear something from the participants. So any participant, 1, 2, or 3, if say something about the today's seminar, whether it is worthy or not, then Department of Chemistry, RANAGHAT College would be obliged for this. Please, any participant, please have 2, 3, 4 words, 3, 4, 5 lines. I request participants.
This was a good session, sir.
Yeah, please, anybody.
This was a very informative session, sir.
Okay, thank you.
Hello.
Yeah,
hello.
sure.
Am I audible?
Yeah. Please.
Okay. First of all, I would like to give a hearty appreciation to the organizing members for arranging such a beautiful webinar. With
Could you please, your name, please?
Okay, I am Arnab Maji from Jadavpur University, Department of Chemistry, and I am a UG student.
Okay.
And so, first of all, I would like to thank organizing members for arranging such a beautiful webinar with a negligible deviation in their schedule. The speakers have delivered their presentation in a very lucid way. But being a UG student, it is very difficult to understand all the materials, but I have got the essence of their talks in a very clear way. That's the important thing. And the most important thing I felt that this webinar helped to make us used to in this type of way of learning, where the digital interaction is the only way to ensure our physical health as well as the mental growth in this unprecedented time. So again, I would like to thank for arranging such a beneficial session for us, and I am really looking forward to attending this type of webinars in near future. Thank you.
Yeah, thank you, man. Thanks. You are a champ student, so you are like my student also. Wherever you are, Jadavpur or in Sibpur or Calcutta or Bardhaman, all are our students. So anybody else, please?
Hello.
Yeah, please.
Hello, sir. Am I audible?
Yeah. Go ahead. Your name, please, and your affiliation.
Sir, I'm Debojyoti Shah from RANAGHAT College, third year student, UG student. So this was a very great webinar, and as Arnab said, it was very much lucid. And what was very much exciting, that is, I got to know a lot of things that I didn't know. So I didn't get the all of things as I'm a UG student, but it was very much helpful to know new things, and it was very good. It was really great webinar to attend.
Okay, thank you.
Thank you, sir.
Yeah, thanks.
Hello, I am
Anybody, please?
I am audible.
Yeah, please, your name and affiliation, please.
My name is Sushrit Shubham Srivastav, and I am a PG student of BHU. It was a very much informative session, and the the quantum heat engines were most favorite ones in the session. And thank you.
Okay. Thank you. Anybody, please? Yes, here, please. Yeah, please. Go ahead.
I am Dr. Kalyani Bitro from
Mhm.
GIS University, Agrawala, Kolkata.
Okay.
Sir, this webinar very nicely organized by host and other organizer. So my gratitude and thanks to all eminent speakers. Nicely express their valuable content easily, smoothly, and clearly. They explain their content of that matter nicely and easily. So this is very nice webinar. I am so very happy to join this type of webinar, and I am anxiously waiting for this type of webinar from RANAGHAT College. Okay, thank you, sir. Thank you all.
Yeah, thank you very much, madam. Thank you.
Okay.
Thanks. It will encourage the child, encourage the students, and it will also motivate us further to organize this kind of seminar. Thank you very much. Anybody, if anybody, please just share your thoughts, just share your feedback. It's a kind of feedback, a kind of notes. If you want to put something, then we'll listen and we will try to improve our next course of action, next seminar when we'll organize. If no, then I have to say a few words about this seminar. Sorry.
Sir, may I audible?
Yeah. Please. Go ahead. Hello.
Second semester of Navadip Bidyasagar College.
Yeah.
And their seminar is really most beautiful and
Sorry, we cannot hear you properly. Hello. Hello.
hello.
Yeah. Please go ahead.
Sir, really their presentation and slide are very nice, and I am
I think it's an internet problem. I mean, connection problem. Anyway, host admin, please make me presenter or in the screen presenter only. Not I don't want to share anything. Just I want to put.
Sir, you are presenter. Sir, you are presenter.
Now I am presenter, right?
Yes, you are already presenter.
Yeah. So I think this is the nobody willing to come here again. I mean, this the feedback session over. Any participant, anybody would like to share something? Okay, if not, then I must say some few words about this seminar, a kind of vote of thanks. So I myself, Habibur Rahman, Assistant Professor of Chemistry, RANAGHAT College. I just want to say a vote of thanks to all of you. So, Honorable Principal, respected IQAC Coordinator, our most valued invited guests, and my colleagues, students, ladies and gentlemen. So, am I audible to all of you?
Yes, sir.
Okay. So, an event like this cannot happen overnight, right? The wheel start rolling weeks ago. It's require planning and a kind of bird's eye for details. We have been fortunate enough to be backed by a team of very motivated and dedicated colleagues of this institution who know their job and these are very result oriented. I cannot thank everyone enough for their involvement and their willingness to take on the complete task of this seminar beyond their comfort zones. It's my privilege to have been asked to propose a vote of thanks on this occasion. I, on behalf of this department, RANAGHAT College, and on my own behalf, extend a very hearty vote of thanks to all the speakers for delivering their important work and sharing their findings and opportunities and their opinions today. A big thank you to Dr. Arnab Ghosh, Dr. Somnath Bakshi, Dr. Taposh Ghosh for making excellent presentation and making this seminar interesting and very, very meaningful. I must mention my deep sense of appreciation for the speakers for giving an excellent coverage to their topic, which are very much relevant with the chemistry knowledge, very much relevant with the chemistry biology interface, and also very much relevant to the current synthetic chemical biology topic. I also wish to express my gratitude to all the speakers for their contribution during this difficult pandemic time. I would like to express my profound gratitude to my principal, Dr. Arup Kumar Maiti, for his presence and support in this seminar. I would also like to thank our HOD, Dr. Sapun Maji, for his moral support and guidance. I am happy to express a word of thanks to my colleagues, my staff members, who have made this seminar a very good and a very grand success. A special thanks to the Cisco WebEx team, especially Tapus Babu, for his enormous help to organize this seminar. And I must convey my thanks and regards to Dr. Nobu Kumar Bira for helping us to prepare this seminar by inviting few distinguished guests. And I mean, one of the speakers who attended this seminar from IIT Kanpur is actually a student of Dr. Abira. So I am very much grateful to him also. Finally, thanks to the wonderful students and the participants who have turned up in such great numbers, not only from our college, but also from other colleges, university, and institution. Thank you so much for your kind help and cooperation. Once again, I thank all for your cordial cooperation. Thank you all. And with this word, this seminar ends here.
Okay, sir. Can I end this now?
Yeah, sure, please.
Thank you, sir.
Hey, just a minute.
Okay. Okay.
So I think participants received the feedback form, right?
Hello, sir.
Yes, sir. Already.
Okay.
Hello.
Already sent in chat box.
Hello,
Okay.
sir.
Yeah. Please go ahead. Who is this?
Sir, I'm Oricha Shikdar from RANAGHAT College.
Yeah.
I'm very happy as the participants.
Uh-huh.
Being a chemistry student, it is very difficult to understand all of the biological information. Still, it was very interesting. Thank you, sir. Thank you very much, sir.
Yeah, thank you. Thank you, my dear students.
Okay, sir.
Yeah, please.
It's over.
Yeah, I think it's over.
Okay. I end this meeting now.